Imagine that you are floating in space, where there is no up or down, only an infinite darkness dotted with lights. You feel a cold that is not just a lack of heat, but a profound emptiness, a presence of absolute nothing that seeps into the very idea of existence. Before you, something unimaginable emerges from this void, a planet with oceans of liquid diamonds and rain of pure iron. The universe holds worlds so strange that human imagination could never have conceived them. There are planets where a day lasts longer than a year, places where the atmosphere would crush you before you could scream. There are huge gas giants with storms raging for thousands of years, and worlds that resemble our Earth, at least at first glance, but are fundamentally, irrevocably alien. These distant worlds may hold the answer to the question of whether we are truly alone in the universe, or if we are just one note in a vast cosmic symphony. This journey begins not with a single planet, but in the cold, dark nurseries where all worlds are born. In the vast, silent gulfs between the stars, great clouds of interstellar gas and dust drift like cosmic ghosts. These are nebulae, and they are not empty voids, but the fertile grounds from which new worlds are born. These colossal structures, some spanning hundreds of light years, are the remnants of previous generations of stars. When massive stars reach the end of their lives, they explode in brilliant supernova, scattering the elements they forged in their nuclear hearts: carbon, oxygen, iron, all the building blocks of life and planets into the surrounding space. These elements enrich the primordial hydrogen and helium that have existed since the early moments of the universe, creating a complex chemical soup for millions of years. These clouds can drift in a delicate balance between the inward pull of their own gravity and the outward pressure from the heat of nearby stars and the subtle forces of their own internal motions. But this tranquility is not eternal. A disturbance, like the shockwave from another nearby supernova or the gravitational nudge from a passing star, can disrupt this balance, causing a region within the cloud to begin to collapse. As this dense core of gas and dust contracts under its own gravity, it begins to heat up and spin faster, conserving its angular momentum just as an ice skater spins faster when she pulls in her arms. At the center of this collapsing cloud, the material becomes so hot and dense that a protostar ignites, a stellar embryo not yet hot enough to begin nuclear fusion. It glows with a deep red light, its energy coming from the heat of gravitational contraction alone. Around this newborn protostar, a rotating disk of the remaining gas and dust forms, a structure known as a protoplanetary disk. This is the birthplace of planets. It is a cosmic potter's wheel, a swirling vortex of material from which new worlds will be sculpted over millions of years. This disk is not uniform. The intense heat from the young star creates a temperature gradient. In the inner regions of the disk, closer to the protostar, it is too hot for volatile substances like water, ammonia, and methane to condense into ice. Only materials with high melting points, such as metals like iron and nickel and rocky silicates, can survive. This region is known as the rock line. Further out, beyond a boundary called the snow line or frost line, the temperature is low enough for those volatile compounds to freeze into solid ice particles. This distinction is crucial for understanding the architecture of a planetary system. In the inner part of the disk, small dust particles, remnants of the initial cloud, begin to stick together through electrostatic forces, like dust bunnies forming under a bed. Over time, these small clumps grow into larger and larger objects through a process called accretion. They collide and merge, forming pebbles, then kilometer-sized rocks called planetesimals. These planetesimals are the building blocks of planets. Their own gravity becomes strong enough to attract more material, and through a chaotic series of collisions, they gradually sweep up the material in their orbits, growing into protoplanets, and finally, into full-fledged rocky planets like Mercury, Venus, Earth, and Mars. In the outer regions of the disk, beyond the snow line, the story is different. Not only are metals and rocks available, but there is also a vast reservoir of ice. This means there is much more solid material to work with, allowing for the formation of much larger planetary cores, perhaps 10 times the mass of Earth. Once these cores reach a critical mass, their gravity is so strong that they can begin to rapidly accrete the abundant hydrogen and helium gas from the surrounding disk. This process of runaway gas accretion forms the gas giants, like Jupiter and Saturn, and the ice giants, like Uranus and Neptune. These outer giants, in turn, have a profound influence on the entire system. Their immense gravity can sling planetesimals and comets around, some into the inner solar system, delivering water and organic molecules to the young rocky planets, and others out of the system entirely. However, each planetary system is unique, a product of the specific conditions of its birth and the chaotic dance of gravitational interactions that followed. Astronomers have discovered systems where giant planets, so-called hot Jupiters, orbit much closer to their star than Mercury does to the Sun, a configuration that was once thought to be impossible. These giants likely formed further out and then migrated inward, disrupting the orbits of any smaller planets in their path. We have found worlds that orbit two stars at once, and even planets that have been ejected from their systems and now wander through the cold darkness of interstellar space alone. The diversity of planets in our universe is astounding and constantly surprises us. Our own solar system is just one of many configurations that the universe creates, a particular outcome of a cosmic lottery played out over billions of years. And with every new telescope and every new method of observation, we discover more and more fascinating worlds waiting to be explored. These are not just distant points of light, they are the products of the same cosmic processes that created our own home, each with its own story, its own history, and its own potential. Closest to our sun orbits a small, scorched world that resembles a long-forgotten stone thrown into a fire. Mercury, named after the swift-footed messenger of the Roman gods, is the smallest planet in our solar system and also the fastest. It whips around the sun in just 88 Earth days, its velocity a constant battle against the star's immense gravitational pull. This planet is a world of extremes, a place of violent contrasts sculpted by its proximity to the solar furnace. During a single languid Mercurian day, which lasts approximately 176 Earth days, the temperatures on the sun-baked surface rise to a staggering 430 degrees Celsius, hot enough to melt lead and tin. But as the long night finally descends, with no substantial atmosphere to trap the heat, the temperature plummets to a cryogenic minus 180 degrees Celsius. This temperature swing of over 600 degrees is the most extreme of any planet in our solar system. If you were to walk on the surface of Mercury, you would see a landscape eerily similar to our moon, a desolate, ancient terrain pockmarked with countless craters, scars from billions of years of bombardment by asteroids and comets. The sky here is always a deep, star-filled black, because Mercury has only a tenuous exosphere, a thin veil of atoms blasted off its surface by the solar wind, far too thin to scatter sunlight. The sun would appear nearly 3 times larger in the sky than we see it from Earth, a blinding, terrifying orb whose unfiltered radiation would instantly burn you. But Mercury is not just a barren desert without interest. In one of the solar system's most beautiful paradoxes, at its poles, in the permanent shadows of deep craters where sunlight never reaches, there is water ice. On one of the hottest planets, you can find frozen water. This ice, confirmed by the Messenger spacecraft, could have been delivered there by cometary impacts over billions of years, or it could have been formed by chemical reactions involving hydrogen from the solar wind. These deposits of ice, protected from the sun's glare and eternal darkness, could be a vital resource for future human exploration. One of the strangest properties of Mercury is its rotation, which is locked in a unique 3-2 spin-orbit resonance. While it orbits the sun in 88 days, it rotates on its axis exactly 3 times for every 2 orbits. This means that on Mercury, a solar day, the time from one sunrise to the next, lasts for 176 Earth days, which is exactly 2 Mercurian years. This peculiar dance with the sun creates a bizarre visual effect. An observer on the surface would see the sun rise, move across the sky, then appear to slow down, stop, move backward for a short time, and then resume its forward motion, a phenomenon known as a double sunrise. Scientists have also revealed that Mercury has an unusually large iron core, which takes up approximately 85% of the planet's volume. For comparison, Earth's iron core makes up only about 17% of its volume. This disproportionately large core suggests that Mercury may have suffered a cataclysmic event in its distant past. One theory proposes that a massive collision with another protoplanet stripped away much of its original rocky mantle, leaving behind the dense, iron-rich remnant we see today. Another idea is that the intense solar wind from a young, more active sun simply vaporized and blew away the lighter materials of its outer layers. This giant iron core is also responsible for Mercury's magnetic field. While much weaker than Earth's, it is still a puzzle, as a planet this small should have cooled and solidified its core long ago, shutting down the dynamo that generates a magnetic field. The existence of this field suggests that part of Mercury's core may still be molten. Despite its relative proximity to Earth, we know less about Mercury than about many more distant planets. Its exploration is difficult due to the sun's intense gravity, which makes it hard for a spacecraft to enter into orbit, and its blinding glare, which complicates observation from terrestrial telescopes. So far, only 2 missions have visited it, Mariner 10 in the 1970s, which performed 3 brief flybys, and the Messenger probe, which orbited it from 2011 to 2015, mapping its surface and revealing many of its secrets. A new mission, Bepi Colombo, a joint venture between the European and Japanese space agencies, is currently on its way and will enter orbit in 2025, promising to unveil even more of the mysteries of this small, swift, and strange world. In the morning and evening hours, we can often observe a glittering point of light in the sky, a beacon so bright that people for millennia have called it the morning star or the evening star. Venus, named after the Roman goddess of love and beauty, is our closest planetary neighbor and in many ways resembles Earth. It has almost the same size, mass, and density as our planet. That is why it is often called Earth's sister, or its twin. But appearances are deceiving. While Earth is a blue oasis of life, a world of temperate climates and liquid oceans, Venus is a hellscape, a toxic inferno where a human would not survive for even a minute. Its atmosphere is a crushing 90 times denser than Earth's, composed almost entirely of carbon dioxide, which creates an extreme and more runaway greenhouse effect. The temperatures on the surface are a uniform 460 degrees Celsius, hotter than the surface of Mercury, despite being nearly twice as far from the sun. It is hot enough to melt lead, and this temperature is constant across the entire planet, from the equator to the poles, day and night. On Venus, it constantly rains, but it is not a refreshing shower of water. The thick yellowish clouds that perpetually shroud the planet are made of sulfuric acid. These corrosive drops fall from the upper atmosphere but never reach the surface. They evaporate in the hellish heat of the lower atmosphere, creating a cycle of acid rain that never ends. If you could walk on the surface of Venus, you would see a dim, orange-tinted sky and a desolate landscape of vast volcanic plains and crumpled mountain ranges. The immense pressure of the atmosphere would crush you with the force of being a kilometer deep in Earth's oceans. The air is so thick that it behaves more like a fluid than a gas, and the landscape is scoured by slow but powerful winds. The surface of Venus is a testament to a violent volcanic past. It is covered in thousands of volcanoes, more than any other planet in the solar system, including massive shield volcanoes and strange, pancake-like domes formed by viscous lava. The entire surface appears to have been repaved by massive volcanic eruptions in a global cataclysm about 500 million years ago, an event that wiped out any earlier craters and reset the planet's geological clock. What is fascinating is that Venus rotates in the opposite direction to most of the planets in the solar system, a phenomenon known as retrograde rotation. And its rotation is incredibly slow. One day on Venus lasts for 243 Earth days, which is longer than its year, which has 225 Earth days. This means that on Venus, a day lasts longer than a year. The sun rises in the west and sets in the east, but a full day-night cycle takes more than a third of an Earth year. The reason for this slow, backward spin is a mystery. It may have been caused by a massive impact in its early history, or perhaps by the long-term effects of its thick atmosphere, creating tidal forces with the planet's solid body. But it was not always like this. Many scientists believe that Venus may have once been a much more hospitable place, a true sister to the early Earth. Billions of years ago, It may have had oceans of liquid water and a milder climate, potentially with conditions suitable for the emergence of life. So, what went wrong? The leading theory is that Venus was a victim of a runaway greenhouse effect. Being slightly closer to the Sun, it received more solar radiation. As the young Sun gradually increased its luminosity, the surface waters on Venus began to evaporate at an accelerated rate. Water vapor is a potent greenhouse gas. So, as more of it entered the atmosphere, the planet began to heat up even more. This, in turn, led to the evaporation of more water, creating a vicious feedback loop. Eventually, the oceans boiled away entirely. In the upper atmosphere, the intense ultraviolet radiation from the Sun broke the water molecules apart into hydrogen and oxygen. The light hydrogen atoms escaped into space, while the oxygen reacted with carbon in the rocks, which was then released into the atmosphere as carbon dioxide through volcanic activity. Without oceans to dissolve the carbon dioxide and lock it away in carbonate rocks, as happens on Earth, it accumulated in the atmosphere, creating the thick, suffocating blanket we see today. Venus is a stark warning for us. It shows how fragile the balance that keeps a planet habitable can be. It is a reminder of how dramatically a planet's climate can change when its delicate balance is disturbed by even a small change in its energy budget. And it is also a testament to how different the fates of two very similar planets can be when they evolve under slightly different conditions. When you look at that shining dot in the evening sky, remember that you are observing a world that could have been very similar to ours, but took a different, tragic path, a path that turned a potential paradise world into a hellish furnace where no terrestrial life can exist. Imagine if you could move away from Earth, past the orbit of the Moon, and observe it from space. What would you see? A blue pearl suspended in the blackness of the cosmos, a swirl of white clouds and brown continents against a backdrop of deep blue oceans. It is a sight of breathtaking fragility and vibrancy, a living world in the vast, silent emptiness. Our planet is, in many ways, an anomaly, a precious exception in a solar system of extremes. It is the only place we know for certain that hosts life, a complex, interconnected web of biology that has transformed its surface, its oceans, and its atmosphere over billions of years. How is this possible? What confluence of factors makes our planet so special, a true habitable world? Let's start with its position, a factor of cosmic real estate. Earth orbits the Sun in the so-called habitable zone, a region sometimes referred to as the Goldilocks zone, where it is not too hot and not too cold for liquid water to exist on the surface. This is a crucial ingredient for life as we know it. Water is a remarkable molecule. Its ability to act as a universal solvent allows it to transport nutrients and facilitate the complex chemical reactions that are the basis of biology. On Earth, we have all three of its states: solid ice, liquid water, and gaseous vapor, which is unique in our solar system and allows for a dynamic water cycle that shapes our climate and ecosystems. But simply being in the habitable zone is not enough, as the fate of Venus demonstrates. Our atmosphere is another key element of our planet's habitability. It is a perfectly balanced, multi-layered shield, a thin, fragile bubble that separates us from the vacuum of space. Composed of 78% nitrogen, 21% oxygen, and trace amounts of other gases like argon and carbon dioxide, it provides the air we breathe, protects us from the sun's harmful ultraviolet radiation through its ozone layer, and maintains a relatively stable and pleasant temperature through a moderate greenhouse effect. The presence of so much free oxygen is itself a sign of life. Oxygen is a highly reactive element, and without its constant replenishment by photosynthetic organisms like plants and algae, it would quickly react with rocks and other elements and disappear from the atmosphere. The Great Oxidation Event, which occurred about 2.4 billion years ago, was a pivotal moment when early life fundamentally remade the chemistry of our planet. We cannot forget the Earth's magnetic field, an invisible guardian generated by the convection of molten iron in the planet's liquid outer core. This geodynamo creates a protective bubble around Earth called the magnetosphere, which extends thousands of kilometers into space. The magnetosphere deflects the solar wind, a constant stream of charged particles flowing from the sun. Without this shield, the solar wind would gradually strip away our atmosphere, as it did on Mars, and bombard the surface with lethal radiation. The interaction of the solar wind with the magnetosphere also creates the beautiful auroras, the northern and southern lights, a visible reminder of the cosmic forces at play. It is also interesting that we have an unusually large moon relative to the size of our planet. The moon's gravitational pull stabilizes the tilt of the Earth's axis, which is currently about 23.5 degrees. This stability ensures predictable seasons and prevents wild swings in climate that would occur if our planet wobbled erratically like a spinning top. The moon also causes the ocean tides, which create rich, dynamic intertidal zones that may have been crucial for the transition of life from the sea to the land. Our moon likely formed after a catastrophic collision between the young Earth and a Mars-sized protoplanet, an event that would have completely reshaped our world's early history and composition. Earth is also geologically active. Its surface is broken into tectonic plates that slowly move across the mantle, crashing into each other to form mountains, pulling apart to create new ocean floor, and subducting to recycle crust back into the interior. This process, the plate tectonic cycle, is vital for long-term climate stability. It is part of the carbonate-silicate cycle, which acts as a global thermostat. Volcanic activity releases carbon dioxide into the atmosphere, warming the planet, while the weathering of silicate rocks removes it, cooling the planet. This feedback loop has helped to keep Earth's climate relatively stable over geological timescales, despite changes in the sun's luminosity. And then there is the water itself. Over 70% of the Earth's surface is covered by oceans, which act as a massive heat reservoir, moderating global temperatures and driving weather patterns. The oceans provide a stable environment for a vast diversity of life and play a key role in the carbon cycle, absorbing a significant portion of the carbon dioxide we emit. All these factors, the right distance from the right kind of star, the right size, the right composition, the presence of a large moon, a magnetic field, plate tectonics, and abundant liquid water have come together to create a delicate and resilient system that has allowed for the existence of life in its astounding diversity. From microscopic bacteria in the deep-sea vents to the complex ecosystems of the rainforests, Earth pulses with life in all its corners. But this balance is not a given. It is the result of 4.5 billion years of coevolution between a planet and its biosphere, and it can be easily disrupted. When we look at our planetary neighbors, Venus and Mars, we see worlds that may have once resembled a young Earth, but their evolution took a different path. They are bookends to our own story, a reminder of how precious and fragile our blue-green home is in the vastness of the cosmos. The red planet, as Mars is often called, has always held a special place in the human imagination. Its distinct reddish hue, visible even to the naked eye as it wanders across the night sky, is reminiscent of blood and fire. It is no wonder that ancient civilizations, from the Babylonians to the Romans, named it after their gods of war. For centuries, Mars has fueled fantasies about extraterrestrial life, from H.G. Wells's Invading Martians to Edgar Rice Burroughs' romantic tales of a dying world. The reality of Mars, as revealed by a fleet of robotic explorers, is just as fascinating. Though different from these fantasies, it is a world of stark beauty and dramatic contrasts, a place that was once much more like Earth, and a prime target for our own future as a multiplanetary species. Mars is a world of superlatives. It is home to the highest mountain in the solar system, Olympus Mons, a colossal shield volcano that rises to a height of almost 27 kilometers, nearly 3 times the height of Mount Everest. Its base is so vast that it would cover the entire state of Arizona. It is also home to the deepest canyon, Valles Marineris, a system of canyons that stretches for over 4,000 kilometers along the Martian equator, dwarfing Earth's Grand Canyon. Mars itself is smaller than Earth. It has about half the diameter and only a tenth of its mass. Its gravity is just 38% of Earth's, which means you would weigh much less there and could leap 3 times as high. A day on Mars, known as a sol, lasts just a little longer than on Earth, at 24.7 hours. But a Martian year is almost twice as long, lasting 687 Earth days, leading to long, drawn-out seasons. When you look at the surface of Mars today, you see mostly a cold, dry, dusty wasteland. The atmosphere is incredibly thin, less than 1% the density of Earth's, and is composed mainly of carbon dioxide. The tenuous atmosphere provides little protection from solar radiation and is too thin to trap much heat. As a result, temperatures are extreme, ranging from a relatively pleasant 20 degrees Celsius on a summer day at the equator to a frigid minus 140 degrees Celsius at the poles during the winter night. But it was not always this way. There is now overwhelming evidence that Mars was once a much warmer and wetter world, a place far more similar to Earth. Robotic missions like the Spirit, Opportunity, Curiosity, and Perseverance rovers have discovered a wealth of geological evidence for a watery past. We have seen ancient river deltas, like the one at Jezero Crater being explored by Perseverance, dried up lake beds, and minerals that could only have formed in the presence of liquid water. There is evidence of massive outflow channels carved by catastrophic floods and possibly even the shoreline of a vast ancient ocean that may have covered much of the planet's northern hemisphere. So, where did all that water go? Some of it is still on Mars today, locked away as ice in the polar caps, which are a mix of water ice and frozen carbon dioxide, and as subsurface ice deposits, but most of it was likely lost to space. Unlike Earth, Mars does not have a global magnetic field to protect its atmosphere from the solar wind. While it may have had one in its early history, the planet's small size meant its core cooled and solidified faster than Earth's, and the protective geodynamo shut down. Over billions of years, the solar wind has been stripping away the Martian atmosphere, particle by particle. As the atmosphere thinned, the pressure dropped, and liquid water on the surface either evaporated or froze, leaving behind the cold, arid desert we see today. Nevertheless, Mars remains one of the most promising places in our solar system to search for traces of past life. If life ever arose on Mars during its warmer, wetter period, it could have left behind fossilized evidence in ancient lake sediments or other geological formations. The primary mission of the Perseverance rover is to collect rock samples from promising locations that a future mission could return to Earth for detailed analysis. It is even possible that microbial life could persist on Mars today, perhaps in subsurface brines or other protected niches where liquid water might still exist intermittently. Mars is also the most likely target for future human settlement. Its relative proximity to Earth, the presence of water ice, an atmosphere that could potentially be used to produce oxygen and rocket fuel, and relatively mild conditions compared to other planets make it the #1 candidate for creating the first extraterrestrial human colony. Imagine the day when humans walk on the red plains of Mars, look up at a pale pink sky, and watch two small, irregularly shaped moons, Phobos and Deimos, fly overhead. It would be a monumental achievement, a new chapter in human history, transforming us from a single-planet species into true citizens of the solar system. Beyond the asteroid belt, which forms a rocky demarcation line between the inner and outer solar system, lies the undisputed king of the planets Jupiter. This gas giant is a true colossus, a world on a scale that is difficult to comprehend. It is more than twice as massive as all the other planets in our solar system combined. Over 1,300 Earths could fit inside its volume. Its presence has significantly influenced the evolution of the entire solar system, and it is sometimes described as a failed star, although it would need to be about 80 times more massive to ignite thermonuclear fusion in its core. Jupiter is a world of breathtaking beauty and violence, a swirling, dynamic canvas of atmospheric phenomena. When you look at Jupiter through a telescope, you are greeted by a stunning sight of alternating light and dark bands of clouds that encircle the planet. The light-colored bands are called zones, and the dark ones are called belts. These are formed by powerful jet streams blowing in opposite directions at speeds of up to 500 kilometers per hour, driven by the planet's incredibly rapid rotation and the heat rising from its interior. Jupiter rotates faster than any other planet in our solar system. One day there lasts less than 10 hours. This rapid spin causes the planet to be visibly flattened at the poles and bulging at the equator, a shape known as an oblate spheroid. This rotation also contributes to the churning, chaotic weather patterns that dominate its atmosphere. The most prominent feature on Jupiter, its iconic emblem, is the Great Red Spot, a colossal anticyclonic storm that has been raging for at least 350 years. since astronomers like Robert Hooke and Giovanni Cassini first observed it with their primitive telescopes. This storm is so large that 2 or 3 Earths could fit inside it. It is a vast, high-pressure system, a hurricane whose winds at its edge reach speeds of over 600 kilometers per hour. Its deep red color is still a mystery, possibly caused by complex organic molecules or sulfur compounds being dredged up from deeper in the atmosphere and colored by solar ultraviolet radiation. The Great Red Spot is not alone. Jupiter's atmosphere is dotted with countless other storms and vortices, some white, some brown, creating a meteorological masterpiece. Jupiter does not have a solid surface like Earth. If you were to descend into its atmosphere, you would find yourself falling through progressively denser and hotter layers of clouds. First ammonia ice, then ammonium hydrosulfide, and finally water ice and vapor. The pressure and temperature would increase dramatically. At a certain depth, about 1,000 kilometers below the cloud tops, the pressure becomes so extreme, over 2 million times Earth's atmospheric pressure, that hydrogen, the main component of Jupiter's atmosphere, undergoes a phase transition. The electrons are squeezed out of the hydrogen atoms, and it begins to behave like a liquid metal, capable of conducting electricity. This vast ocean of metallic hydrogen is believed to be the source of Jupiter's immensely powerful magnetic field, which is nearly 20,000 times stronger than Earth's and creates a magnetosphere so large that if it were visible, it would appear larger than the full moon in our night sky. This magnetosphere traps charged particles from the solar wind, creating the most intense radiation belts in the solar system. These belts are so powerful that they would be lethal to an unprotected astronaut in minutes and pose a significant challenge for any spacecraft sent to study the planet. The interaction of these trapped particles with Jupiter's atmosphere also creates breathtaking auroras at its poles, far more energetic and extensive than those on Earth. Jupiter also plays an important role in our solar system as a kind of cosmic vacuum cleaner or gravitational shepherd. Its huge gravity has shaped the asteroid belt and has likely protected the inner planets, including Earth, from a more intense bombardment of comets and asteroids by either capturing them or ejecting them from the solar system. The most famous example of this protective effect was the collision of comet Shoemaker-Levy 9 with Jupiter in 1994. The comet was torn apart by Jupiter's gravity, and its fragments crashed into the planet's southern hemisphere, leaving behind a string of dark scars, some larger than the Earth, a dramatic reminder of Jupiter's role as our solar system's guardian. At least 95 moons are known to orbit Jupiter, forming a miniature solar system of their own. The 4 largest of these, the Galilean moons, were discovered by Galileo Galilei in 1610, a discovery that was instrumental in overthrowing the geocentric model of the universe. Each of these moons is a unique world worthy of separate study. Io is the most geologically active body in the solar system, its surface constantly repaved by hundreds of active volcanoes spewing sulfur and silicate lava, driven by the immense tidal forces from Jupiter's gravity. Europa, a world slightly smaller than our moon, is covered by a smooth, icy crust, beneath which lies a global ocean of liquid salt water, thought to contain more water than all of Earth's oceans combined. This subsurface ocean, kept liquid by tidal heating, is considered one of the most promising places in our solar system to search for extraterrestrial life. Ganymede is the largest moon in the solar system, larger even than the planet Mercury, and is the only moon known to have its own magnetic field. Callisto, the outermost of the Galilean moons, is a heavily cratered, ancient world, its surface a frozen record of the history of the early solar system. Jupiter and its family of moons represent a system of incredible complexity and diversity, a laboratory for studying planetary science and a prime target in our quest to understand the potential for life beyond Earth. When Galileo Galilei first pointed his simple telescope at Saturn in 1610, he was confused by what he saw. The planet appeared to have 2 ears, or handles, on its sides, strange appendages that he could not explain. It was not until 45 years later that the Dutch astronomer Christiaan Huygens, with a more powerful telescope, correctly determined that these formations were actually a system of rings surrounding the planet, a flat, thin disk that was not touching it. Today, we know that Saturn is adorned with the most beautiful and extensive system of rings in the solar system, a feature of such elegance and complexity that it makes the planet a true jewel of the cosmos. Saturn is the second largest planet in our solar system, after Jupiter, and like its larger neighbor, it is a gas giant composed mainly of hydrogen and helium. However, Saturn is much less dense. In fact, its average density is lower than that of water. If you could find an ocean large enough, Saturn would float in it. It is the only planet in our solar system with this property. At first glance, Saturn's atmosphere resembles Jupiter's, with bands of clouds encircling the planet, but its colors are more subdued, in pastel shades of yellow, gold, and beige, due to a thicker haze layer in its upper atmosphere. The winds on Saturn are among the fastest in the solar system, reaching speeds of up to 1,800 kilometers per hour at the equator. At Saturn's North Pole, the Cassini spacecraft discovered a bizarre and mesmerizing feature, a stable, hexagonal jet stream, a cloud pattern with 6 straight sides, each side wider than the Earth. The origin of this geometrically perfect formation is still being studied, but it is thought to be a standing wave pattern in the planet's atmospheric currents. But what truly sets Saturn apart are its magnificent rings. They extend from about 7,000 to 120,000 kilometers above the planet's equator, yet their thickness is astonishingly small, in most places only a few tens of meters. They are composed of billions of particles of almost pure water ice, ranging in size from microscopic dust grains to boulders the size of houses. These particles orbit the planet at incredible speeds, creating a complex and dynamic structure with thousands of individual ringlets, gaps, and density waves, sculpted by the gravitational influence of Saturn's many moons. The major rings are labeled with letters in the order of their discovery. The brightest and most prominent are the A and B rings, which are separated by the Cassini division, a gap about 4,800 kilometers wide that is visible even in amateur telescopes. The origin of the rings has long been a mystery. They could have formed from the breakup of a moon or a captured comet that came too close to Saturn and was torn apart by its immense tidal forces, a region known as the Roche limit. Or they could be the primordial remnants of the material from the nebula from which Saturn itself formed, material that never managed to coalesce into a moon. Data from the Cassini mission surprisingly suggested that the rings are relatively young, perhaps only 100 million years old, meaning they may have formed during the age of the dinosaurs on Earth. This finding is still debated, but it suggests that planetary rings may be a transient, rather than a permanent, feature. Saturn also has a rich and diverse family of at least 83 known moons, ranging from small, irregularly shaped rocky bodies to giant worlds. The largest of these, Titan, is a world of extraordinary interest. It is larger than the planet Mercury and is the only moon in the solar system with a dense, substantial atmosphere, even denser than Earth's. Titan's atmosphere is composed mainly of nitrogen, like our own, but it also contains methane and other organic compounds. The conditions on Titan are so cold, around minus 180 degrees Celsius, that methane can exist as a liquid, solid, and gas, playing a role similar to water on Earth. The Cassini-Huygens mission revealed a stunning landscape on Titan, with rivers, lakes, and seas of liquid methane and ethane, making it the only body besides Earth that we know of that has stable liquid on its surface. It is a strange, alien version of our own world, a place where it rains methane and the riverbeds are carved by liquid hydrocarbons. Another of Saturn's moons, the small, icy Enceladus, has turned out to be one of the most exciting places in the solar system. Despite its small size, it is geologically active. The Cassini spacecraft discovered huge geysers erupting from cracks near its south pole, spewing plumes of water vapor, ice crystals, and organic molecules into space. This discovery is strong evidence for a global ocean of liquid water lurking beneath its icy crust, kept warm by tidal heating from Saturn's gravity. The presence of liquid water, organic molecules, and a source of energy makes Enceladus a prime candidate in the search for extraterrestrial life. When you look at Saturn through a telescope, you are not just seeing a beautiful object. You are observing a complex and dynamic system, a world of incredible storms, ephemeral rings, and moons that could potentially harbor life, a true gem of our solar system. Far beyond the orbit of Saturn, in the cold, dim outer regions of our solar system, lie two worlds that are significantly different from the other planets. Uranus and Neptune are often referred to as ice giants, a distinct class of planet from the gas giants Jupiter and Saturn. While Jupiter and Saturn are composed almost entirely of hydrogen and helium, Uranus and Neptune are made up of a much higher proportion of heavier elements, or ices, such as water, ammonia, and methane. These materials are not frozen solid in the way we think of ice on Earth. In the planet's interiors, under extreme pressures and temperatures, they form a hot, dense, electrically conductive fluid, a kind of supercritical ocean surrounding a small, rocky core. Uranus was the first planet to be discovered with a telescope. In 1781, the British astronomer William Herschel was systematically scanning the sky when he spotted a faint object that he initially thought was a comet. After further observation, it became clear that it was a new planet, the first to be discovered since antiquity, doubling the known size of the solar system. Uranus is the third largest planet by diameter and the fourth most massive. On a clear, dark night, under ideal conditions, it is just at the edge of visibility for the naked eye. But its faintness and slow movement across the sky meant it was overlooked for millennia. The most remarkable and bizarre feature of Uranus is its extreme axial tilt. While other planets spin more or less upright as they orbit the sun, like spinning tops, Uranus is tilted on its side, with its axis of rotation lying almost in the plane of its orbit, at an angle of nearly 98 degrees. This means that it essentially rolls along its orbital path. This extreme tilt leads to the most extreme seasons in the solar system. During its 84 Earth-year orbit, each pole gets 42 years of continuous sunlight, followed by 42 years of continuous darkness. The reason for this peculiar orientation is thought to be a cataclysmic collision with an Earth-sized protoplanet during the chaotic early history of the solar system. Such a massive impact would have been powerful enough to knock the young planet over on its side. Uranus has a faint system of dark rings, discovered in 1977, and is orbited by 27 known moons, which are uniquely named after characters from the works of William Shakespeare and Alexander Pope, rather than from Greek or Roman mythology. Neptune, the last of the major planets, has a discovery story that is a triumph of theoretical physics. After the discovery of Uranus, astronomers noticed that its orbit was not quite what Newton's laws of gravity predicted. There were slight perturbations, suggesting that the gravity of an unknown, more distant planet was tugging on it. In the 1840s, two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently used these perturbations to calculate the position of the hypothetical planet. In 1846, Le Verrier sent his prediction to the Berlin Observatory, and on the very first night of searching, the astronomer Johann Galle found Neptune within 1 degree of the predicted position. It was a stunning confirmation of the power of Newtonian physics. Neptune is the smallest of the giant planets, but it is denser than Uranus and has a stronger gravitational pull. It is also the coldest of the major planets, with cloud-top temperatures dropping into around -220 degrees Celsius. Despite this, and despite receiving only a tiny fraction of the sunlight that Jupiter does, Neptune's atmosphere is surprisingly dynamic and turbulent. When the Voyager 2 spacecraft flew by Neptune in 1989, it captured images of the Great Dark Spot, a huge storm system similar to the Great Red Spot on Jupiter. The most remarkable feature of Neptune's atmosphere, however, is its winds. The fastest winds in the solar system have been recorded on Neptune, reaching supersonic speeds of up to 2,100 kilometers per hour. The source of the internal heat that drives this extreme weather is still a mystery. Neptune also has a faint, clumpy ring system and is orbited by 14 known moons. The largest of these, Triton, is one of the most fascinating bodies in the solar system. It is a large, icy moon that orbits Neptune in a retrograde direction, opposite to the planet's rotation. This is strong evidence that Triton was not formed with Neptune, but is a captured object from the Kuiper Belt, a vast reservoir of icy bodies beyond the orbit of Neptune. Triton is geologically active, with geysers of nitrogen gas and dust erupting from its surface, and it has a very thin nitrogen atmosphere. Its capture by Neptune would have been a chaotic and violent event, likely destroying Neptune's original system of moons. For almost 8 decades, Pluto was considered the 9th planet in our solar system, a small, icy world at the dim frontiers of our planetary system. It was discovered by the American astronomer Clyde Tombaugh in 1930 at the Lowell Observatory in Arizona, after a painstaking search for a predicted Planet X beyond Neptune for generations. Pluto was the final, mysterious outpost in our solar system. But in the late 20th and early 21st centuries, astronomers began to discover other objects in the outer solar system, in a region called the Kuiper Belt, that were similar in size to Pluto, such as Eris, which was initially thought to be even larger. This raised a problem if Pluto was a planet. Should all these other new objects be planets too? The question came to a head in 2006, when the International Astronomical Union met in Prague and, after a stormy debate, adopted a formal definition of a planet for the first time. According to this new definition, a celestial body must meet 3 criteria to be called a planet. It must orbit the Sun. It must be massive enough for its own gravity to pull it into a nearly round, or hydrostatic equilibrium, shape, and it must have cleared the neighborhood around its orbit, meaning it has become gravitationally dominant, with no other bodies of comparable size other than its own satellites. It was this third condition that proved fatal for Pluto. Pluto orbits in the crowded Kuiper Belt and has not cleared its orbital zone. Therefore, it was reclassified as a dwarf planet, a new category of objects that meet the first 2 criteria, but not the third. This decision sparked not only a scientific debate, but also an emotional reaction from the public. Many people who grew up learning about 9 planets have not accepted this change to this day, but while Pluto may have lost its planetary status, it has gained so much more in our understanding. In 2015, NASA's New Horizons probe, which was launched the same year Pluto was demoted, performed the first ever flyby of this distant world, sending back images that exceeded all expectations. Instead of a dead, inert ball of ice and rock, New Horizons revealed a surprisingly complex and geologically active world. On the surface of Pluto, we discovered a vast, bright, heart-shaped region named Tombaugh Regio, which is a massive glacier of frozen nitrogen. We found towering mountain ranges made of water ice, which at Pluto's frigid temperatures of around -230 degrees Celsius is as hard as rock. We found evidence of flowing nitrogen ice glaciers, a thin, hazy nitrogen atmosphere, and possible cryovolcanoes that may have erupted a slushy mixture of water, ammonia, and methane. This level of geological activity was completely unexpected on such a small, cold world, suggesting that Pluto may have a source of internal heat, perhaps from the radioactive decay of elements in its core, or a subsurface ocean of liquid water. New Horizons also studied Pluto's largest moon, Charon, which is so large in proportion to Pluto, about half its diameter, that they are better described as a binary system, orbiting a common center of gravity that lies in the space between them. Charon also has a fascinating and varied geology, including a huge canyon system that dwarfs the Grand Canyon on Earth. The flyby of Pluto and Charon transformed them from distant, fuzzy points of light into vibrant, complex worlds, the best explored objects in the Kuiper Belt. Pluto's story is a powerful reminder that our classifications are human constructs, and that the universe is full of wonders that defy our neat and tidy categories. For millennia, people only knew about the planets of our own solar system. Philosophers and scientists speculated whether planets orbit other stars, but they had no way of proving it. This changed forever in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of the first planet orbiting a sun-like star outside our solar system. This planet, named 51 Pegasi b, started a revolution in astronomy, opening a new window onto the cosmos. Today, 3 decades later, we know of more than 5,000 confirmed exoplanets, and their number is growing almost daily. These distant worlds are incredibly diverse and often very different from the planets of our solar system. Their discovery has shown us that our solar system is just one of many possible configurations, and that the universe is filled with planetary systems that defy our imagination. The detection of exoplanets is an extraordinary technical challenge. They are incredibly faint compared to their parent stars and are located at immense distances, making them impossible to see directly with most telescopes. It is like trying to spot a firefly next to a brilliant searchlight from hundreds of miles away. To find these hidden worlds, astronomers have developed a suite of clever indirect methods. The most successful of these are the radial velocity method and the transit method. The radial velocity method, which found 51 Pegasi b, takes advantage of the fact that a planet and a star orbit a common center of gravity. As a planet orbits its star, it causes the star to wobble slightly back and forth. We can detect this wobble by observing the star's light. As the star moves toward us, its light is slightly shifted to the blue end of the spectrum, and as it moves away, it is shifted to the red end. This tiny periodic Doppler shift in the star's light reveals the presence of an unseen companion and allows us to estimate its mass. The transit method, which has been responsible for the vast majority of exoplanet discoveries thanks to missions like the Kepler Space Telescope, consists of monitoring the brightness of a star over time. If a planet passes in front of its star from our perspective, an event known as a transit, it will block a tiny fraction of the starlight, causing a slight periodic dip in the star's brightness. This method allows us to determine the planet's size and its orbital period. By combining the transit and radial velocity methods, we can determine a planet's density, which gives us our first clue about its composition. Other methods include gravitational microlensing, which uses the gravity of a star or planet to magnify the light of a more distant star, a technique particularly good at finding free-floating planets, and direct imaging, which involves blocking out the light of a star with a special instrument called a coronagraph to directly see the faint light of the planets orbiting it. This last method is extremely difficult but has been successful in a few cases, giving us our first direct pictures of other worlds. The first discovered exoplanets were mostly so-called hot Jupiters, massive gas giants orbiting extremely close to their stars. This was not because they are the most common type of planet, but because they are the easiest to detect. Their large mass creates a strong gravitational tug, making them easy to find with the radial velocity method, and their large size and short orbital periods mean they cause frequent and deep transits. These strange worlds orbit their stars at extreme proximities, often closer than Mercury is to the Sun, completing one orbit in a few days or even hours. Their atmospheres are heated to thousands of degrees, and some are so close that they are being stripped away by their star's radiation, creating long, comet-like tails of gas. As our technologies improved, we began to discover smaller and more distant planets as well. The Kepler Space Telescope, launched in 2009, was a game-changer. By staring at a single patch of sky in the constellation Cygnus for 4 years, it monitored the brightness of over 150,000 stars, discovering thousands of exoplanets and revealing the statistical prevalence of planets in our galaxy. Kepler's data showed us that planets are incredibly common. On average, there is at least one planet for every star in the Milky Way, which means there could be hundreds of billions of planets in our galaxy alone. One of the most surprising findings from Kepler was that the most common type of planet in our galaxy are those that we do not have in our solar system at all. Super-Earths, planets larger than Earth but smaller than Neptune, and mini-Neptunes, or gas dwarfs, which fall in the size range between Earth and Neptune. The existence of these common types of planets, and their absence in our own solar system, is a major puzzle in planetary science and suggests that our solar system's architecture may be somewhat unusual. The search for exoplanets is not just about cataloging other worlds, it is about understanding our own place in the universe. Each newly discovered planet is another piece of a puzzle that helps us refine our theories of how planets form and evolve. It pushes us to expand our understanding of what is possible, from the fiery hellscapes of lava worlds to the frozen darkness of rogue planets. And, most profoundly, it brings us closer to answering one of humanity's oldest and most fundamental questions: are we alone? The search for Earth-like planets in the habitable zones of their stars, worlds where life as we know it could potentially exist, is now at the forefront of astronomical research, a quest that could change our perception of the universe forever. As we continue to explore the galactic neighborhood, a recurring theme emerges: the sheer, unbridled diversity of worlds. The more exoplanets we discover, the more clearly we see that our own solar system, once the only template we had, is not a typical example of a planetary system, The universe is a far more creative and chaotic architect than we had imagined. One of the most striking findings is that the most common types of planets in our galaxy are those that are conspicuously absent from our own celestial family, the so-called super-Earths and mini-Neptunes. Super-Earths are a class of planets with a mass between that of Earth and Neptune, typically between 1 and 10 times the mass of our own planet. As the name suggests, they are larger than Earth but are thought to be primarily rocky, at least at the lower end of their mass range. It is important to understand that the term super-Earth describes only the planet's size, not its composition or habitability. Some super-Earths may indeed be scaled-up versions of our world, with a solid surface, a thin atmosphere, and potentially liquid water. An example of a potentially rocky super-Earth is Kepler 452b, sometimes dubbed Earth's cousin, which is about 60% larger than Earth and orbits in the habitable zone of a sun-like star. Others, however, could be very different. They might be water worlds, planets with a small rocky core covered by a deep global ocean, or they could have thick, hydrogen-dominated atmospheres that would make their surfaces crushingly hot and uninhabitable. Mini-Neptunes, sometimes called gas dwarfs, are planets that are smaller and less massive than our own ice giants, Uranus and Neptune, but still have a substantial gaseous envelope. They typically have a mass between 10 and 50 times that of Earth. These worlds likely have a large rocky or icy core surrounded by a thick atmosphere of hydrogen, helium, and other volatile gases. A typical example is Kepler 11f, which has a diameter about 2.5 times that of Earth, but is much less dense, suggesting it is not a rocky world, but has a significant atmosphere. The distinction between a large super-Earth and a small mini-Neptune is blurry, and there is likely a continuum of planets between these two categories. The fact that these intermediate-sized planets are so common in the galaxy, yet missing from our solar system, is a profound puzzle. Our solar system has a clear gap. The largest rocky planet is Earth, and the smallest giant planet is Neptune, which is about 17 times more massive than Earth. There is nothing in between. Why? The answer may lie in the chaotic history of our solar system's formation. One leading theory, the Grand Tack hypothesis, suggests that Jupiter, in the early days of the solar system, migrated inward from its formation location, coming as close to the Sun as the orbit of Mars, before being pulled back outward by the gravitational influence of Saturn. This inward and outward journey would have acted like a giant snowplow, disrupting the orbits of the planetesimals and protoplanets in the inner solar system and potentially clearing out the material that would have otherwise formed super-Earths. In this view, our solar system's architecture is a direct result of the specific dance of our giant planets. The existence of super-Earths and mini-Neptunes also forces us to rethink our understanding of planet formation. Traditional models, developed based on our solar system, have had difficulty explaining the existence of these intermediate types of planets. Newer models, which take into account the migration of planets through the protoplanetary disk and the complex interactions between growing planets, are beginning to offer a better explanation for the observed diversity. The study of these common but alien worlds provides us with valuable insight into the processes that shape planetary systems across the galaxy. It also helps us to better understand how exceptional or common our own Earth may be. Perhaps the very architecture that prevented the formation of super-Earths in our solar system was a key factor that allowed for the long-term stability and habitability of our own planet. The diversity of worlds extends far beyond their size. We have found planets with extreme densities. PSR J179-1438b is a planet orbiting a rapidly spinning neutron star, a pulsar. It is so dense that scientists believe it may be the crystalline core of an ancient white dwarf star, composed mainly of carbon and oxygen that has been compressed into a planet-sized diamond. On the other end of the spectrum are the super puffs, planets with the density of cotton candy. Kepler 51b, for example, is a Jupiter-sized planet but has only a tiny fraction of its mass, making it one of the lowest density planets ever discovered. Then there are the planets with the most bizarre orbits. HD 80606b has one of the most eccentric, or elongated, orbits we know of. It spends most of its 111-day year far from its star in a cold, distant region, but then it swings in on a close, scorching pass, causing extreme and rapid temperature changes. The exoplanet TRES 2b is one of the darkest worlds known, reflecting less than 1% of the light that falls on it, making it darker than coal or black acrylic paint. Its atmosphere is thought to contain light-absorbing chemicals like vaporized sodium and potassium. These extreme worlds remind us how diverse and wondrous the universe around us is. They are natural laboratories for testing our understanding of physics under conditions that we could never replicate on Earth. They show us that nature's imagination is far more vast than our own, and they highlight the extraordinary and perhaps rare combination of factors that have made our own planet a stable, temperate, and life-bearing world. When we look at the night sky, we can now imagine that around each of those distant stars orbit worlds that are more different from our own planets than we could have ever conceived. The universe is not just a collection of familiar objects. It is a veritable zoo of cosmic oddities, each one with its own unique story to tell. When we search for the possibility of life beyond Earth, we naturally focus on planets that could have conditions similar to our own home world. A key concept in this search is the so-called habitable zone, a term often used in popular science, but one that is more complex than it might seem. It is traditionally defined as the region around a star where the temperature is just right for liquid water to exist on the surface of a rocky planet with a suitable atmosphere. It is sometimes called the Goldilocks zone, not too hot, not too cold, but just right. The importance of liquid water for life as we know it cannot be overstated. It is a superb solvent, allowing the complex molecules of life to dissolve and interact. It has a high heat capacity, which helps to moderate temperatures, and its solid form, ice, is less dense than its liquid form, which means that lakes and oceans freeze from the top down, insulating the liquid water below. It is no wonder that in the search for life, the mantra of astrobiologists has long been "follow the water." The position and width of the habitable zone depend critically on the type of star. Around hot, bright, massive stars, the habitable zone is farther out and wider. Around cooler, fainter, less massive stars, like red dwarfs, it is much closer to the star and narrower. Our own sun is a G-type star, and its habitable zone is generally considered to extend from somewhere inside the orbit of Venus to just outside the orbit of Mars, with Earth nestled comfortably in the middle. But simply being in the habitable zone is no guarantee of habitability. A planet's ability to support life depends on a host of other factors. The size of the planet is crucial. If it is too small, like Mars, it will have difficulty holding on to a substantial atmosphere and may cool down too quickly, losing its geological activity. If it is too large, it may become a mini Neptune, with a thick, crushing atmosphere unsuitable for surface life. The planet's composition, the presence of a magnetic field to shield it from stellar radiation, and the existence of plate tectonics to regulate its climate over long time scales are all thought to be important factors. The star itself is also a major consideration. While red dwarfs are the most common type of star in the galaxy, and many have been found to host Earth-sized planets in their habitable zones, they also pose significant challenges. They are known for their intense stellar flares, which could strip away the atmospheres of close-in planets and bathe their surfaces in lethal radiation. Also, planets in the habitable zone of a red dwarf are so close to the star that they are likely to be tidally locked, with one side in perpetual daylight and the other in perpetual darkness, creating extreme temperature contrasts. G-type stars like our Sun, or slightly cooler K-type stars, are often considered better candidates for hosting life, as they are more stable and have a longer lifespan. Among the most promising candidates for habitable exoplanets discovered so far is Proxima Centauri b, which orbits the nearest star to our Sun at a distance of only 4.2 light-years. It is a rocky planet only slightly more massive than Earth and orbits within its star's habitable zone. However, its star is an active red dwarf, raising questions about its true habitability. Another exciting system is TRAPPIST-1, located about 40 light-years away. It is an ultra-cool red dwarf orbited by 7 Earth-sized rocky planets. At least 3 of these planets, TRAPPIST-1e, F, and G, are in the habitable zone. TRAPPIST-1e is perhaps the most intriguing. with a size and density very similar to Earth's. The James Webb Space Telescope is currently studying the atmospheres of these planets, searching for clues about their composition and potential for hosting life. Kepler 186f was the first Earth-sized planet discovered in the habitable zone of another star. It is about 10% larger than Earth and orbits a red dwarf star about 500 light-years away. The concept of habitability is also expanding beyond the traditional habitable zone. The moons of giant planets, like Europa and Enceladus in our own solar system, could have subsurface oceans of liquid water, kept warm by tidal heating, far outside the sun's habitable zone. This raises the possibility that habitable moons could be common throughout the galaxy. A special category of potentially habitable worlds are ocean planets or Hycean worlds, planets that have much more water than Earth, and whose surfaces are entirely or mostly covered by a global ocean. These planets could have a wide range of habitable conditions, and some may have hydrogen-rich atmospheres. Life in such worlds would be purely aquatic and could be very different from life on Earth. As we discover more and more exoplanets and improve our methods of analyzing their atmospheres and surfaces, we are moving from simply cataloging other worlds to characterizing them in detail. The search for a second Earth is not just about finding a twin of our own planet. It is about understanding the full range of conditions under which life might be able to arise and thrive in the universe. It is a quest that may, in the coming decades, provide us with one of the most profound answers in the history of science. Our journey through the cosmos has revealed a universe brimming with worlds, a place of far greater diversity and strangeness than our ancestors could ever have dreamed. From the scorched, cratered plains of Mercury to the frozen, distant plains of Pluto, from the swirling storms of Jupiter to the methane seas of Titan, our own solar system is a testament to the varied outcomes of planetary formation. But it is in the realm of exoplanets that the true, bewildering diversity of the universe is revealed. We have found planets that defy our neat classifications and challenge our understanding of what a planet can be. There are hot Jupiters locked in a fiery embrace with their stars, super-Earths that may be scaled-up versions of our own world, and mini-Neptunes that fill a gap in our own solar system's architecture. There are diamond planets, lava worlds, and planets where it rains glass sideways and supersonic winds. There are lonely, wandering planets, cast out from their home systems to drift through the interstellar darkness, and planets that dance a complex waltz around two suns. Each new discovery is like another piece of a grand puzzle, helping us to build a more complete picture of how planets form and evolve. But perhaps the most important question that drives our exploration of these distant worlds is the oldest and most profound of all: are we alone? As we have seen, there are many worlds that could, in principle, have the right conditions for life as we know it. The subsurface oceans of moons like Europa and Enceladus, the ancient riverbeds of Mars where water once flowed, and the many exoplanets found orbiting in the habitable zones of their stars all represent tantalizing possibilities. The sheer number of potentially habitable worlds in our galaxy, perhaps tens of billions of them, suggests that the raw ingredients for life may be common. If life is common, what might it look like? Perhaps it would be microbial, simple organisms thriving in niches protected from the harshness of space. Or perhaps, on some worlds, it has had the time to evolve into complex, multicellular forms, creating ecosystems as rich and diverse as our own. It could be based on the same carbon chemistry and water solvent as life on Earth, or it could be based on completely different principles, a truly alien biology that we can currently only speculate about. Life could exist in the liquid methane of Titan's seas, in the dense atmospheres of gas giants, or even as a form of silicon-based life on a hotter world. The possibilities are as vast as the universe itself. But even non-living worlds offer us fascinating insights. They are natural laboratories where we can study physics under extreme conditions. The volcanic activity on Io, driven by tidal forces, teaches us about geology and heat transfer. The rings of Saturn provide a miniature model for the dynamics of protoplanetary disks. The extreme weather on Neptune challenges our models of atmospheric physics. By studying these other worlds, we learn more about the fundamental laws that govern our universe. What does the future hold for our exploration of these cosmic neighbors with new and more powerful telescopes, like the James Webb Space Telescope and future ground-based observatories, we will be able to probe the atmospheres of more and more exoplanets, searching for the telltale chemical fingerprints of life, or biosignatures. Missions are being planned to return to the ocean worlds of our outer solar system, to land on Europa's ice and perhaps even drill down to its hidden ocean. And humanity is taking its first tentative steps towards becoming a multiplanetary species, with Mars as our first destination. But whatever we discover, one thing is certain: the universe will always be larger, more complex, and more wondrous than we can imagine. Every new answer will bring with it a host of new questions, revealing ever deeper layers of mystery and beauty. As Carl Sagan so eloquently put it, we are a way for the cosmos to know itself. We are the product of cosmic evolution, stardust that has become conscious. In our quest to explore other worlds, we are not just looking outward, we are also looking inward, seeking to understand our own origins and our place in the grand cosmic scheme. So the next time you look up at the night sky, remember that what you see are not just distant points of light, they are other suns, each one a potential center of its own system of worlds, a system that could be as familiar as our own or as alien as our wildest dreams. And somewhere out there, there may be other beings looking up at their own sky and asking the same questions. In this endless dance of cosmic dust and energy, in the constant cycle of the birth and death of stars and planets, we are part of something immensely large and beautiful, children of the stars, and perhaps, one day, we will become citizens of the cosmos.
Imagine a cat, sealed inside a box, its fate tied to the whims of a single radioactive atom. If the atom decays, an event governed entirely by the probabilistic laws of quantum mechanics, a vial of poison is shattered, and the cat dies. If the atom does not decay, the cat lives. According to our classical everyday intuition, the cat inside the box is definitively either one or the other. We simply do not know which until we open the box and look. But this is not what quantum mechanics tells us. It tells us something far stranger, something that strikes at the very heart of our understanding of reality. It tells us that until the moment of observation, the atom exists in a superposition of states it has both decayed and not decayed simultaneously. And because the cat's fate is inextricably linked to the atoms, the cat, too, must exist in a superposition. It is, in the bizarre language of quantum physics, both alive and dead at the same time. A ghostly blend of two mutually exclusive realities coexisting in a single, unobserved space. This is Erwin Schrödinger's famous thought experiment, and it was not designed to be a literal description of feline biology, but rather a dramatic, macroscopic metaphor to expose the profound absurdity and the deep philosophical paradox that arises when the strange rules of the quantum world are scaled up to the world of our everyday experience. We never see a cat that is both alive and dead. The moment we open the box, the moment we make a measurement, this cloud of possibilities, this wave function, collapses into a single, definite reality. The cat is either alive or it is dead. The act of observation seems to be the trigger that forces the universe to make a choice. But how? And why? This is the quantum measurement problem, one of the deepest and most unresolved mysteries in all of science. It forces us to ask a question that feels more philosophical than physical. Does reality exist independently of our observation of it? Or is the universe a participatory one, a reality that only solidifies, only becomes real when a conscious observer, or at least a measuring device, interacts with it? This idea is not just a scientific curiosity, it is a profound challenge to our sense of an objective, external world. It suggests that the boundary between the observer and the observed is not as clear as we once thought, that we are not passive spectators watching a pre-existing cosmic drama, but active participants co-creating the script as we go along. Schrödinger's cat, in its sealed box, becomes a symbol for every unobserved potential, every undecided future, every unexamined corner of our own consciousness. It is a metaphor for the state of our own minds as we drift into sleep. A state where the rigid certainties of the waking world dissolve, where logic and contradiction can coexist, where we are both here and not here, both ourselves and someone else entirely. In the comforting darkness of this quantum uncertainty, we surrender the act of measurement and allow ourselves to float in the pure, uncollapsed sea of possibility, a sea from which all realities, both in the cosmos and in our own minds, are born. The strange state of Schrödinger's cat is built upon the foundational principle of quantum superposition, a concept that is as fundamental to the quantum world as gravity is to the classical one. Superposition dictates that a quantum system, like an electron or a photon, can exist in a combination of multiple, seemingly contradictory states at the same time. As long as it is not being measured, an electron does not have a single, definite position. It exists as a probability wave, a cloud of potential locations spread out over a region of space. It is not here or there. It is, in a sense, both here and there. A photon can be polarized both vertically and horizontally simultaneously. An atom can be in both a high energy and a low energy state at once. This is not a matter of our ignorance. It is not that we simply do not know the particle's true state. The particle's true state is this combination of all possible states. The most famous and elegant demonstration of this is the double-slit experiment. If you fire a single electron at a barrier with two slits in it, and you do not watch to see which slit it goes through, the electron behaves not like a particle, but like a wave. It seems to pass through both slits at the same time, creating an interference pattern on the detector screen behind the barrier, a series of bright and dark bands that is the classic signature of two waves interfering with each other. It is as if the electron's own probability wave splits, passes through both slits, and then interferes with itself. This happens even if you fire only one electron at a time. The single electron, somehow, knows about the existence of both paths and behaves accordingly. However, the moment you place a detector at one of the slits to see which path the electron takes, the magic disappears. The interference pattern vanishes. The electron behaves like a well-behaved particle, passing through one slit or the other, but not both. The very act of measurement, of gaining information about the electron's path, forces it to abandon its wave-like superpositional nature and choose a single, definite reality. This is not just an abstract concept, it is the engine behind the next technological revolution. The power of quantum computers lies in their ability to harness superposition. A classical computer bit can be either a 0 or a 1, but a quantum bit, or qubit, can be a 0, a 1, or a superposition of both at the same time. This allows a quantum computer to perform a vast number of calculations simultaneously, giving it the potential to solve problems that are intractable for even the most powerful classical supercomputers. But perhaps the most fascinating aspect of superposition is its echo in our own subjective experience. As we lie on the edge of sleep, in the hypnagogic state, our minds enter a similar realm of fluid possibility. The rigid categories of waking thought dissolve. We are not fully awake, nor fully asleep. Memories, thoughts, and images from different times and places can coexist and merge in strange and beautiful ways. We can feel both the comfort of our bed and the sensation of floating in a distant, imagined landscape. This is a mental superposition, a state where the mind is no longer collapsed into a single, definite stream of consciousness, but exists as a shimmering cloud of potential experiences. It is in this state that the seeds of our dreams are sown, a state where the strict logic of the classical world gives way to the poetic, associative logic of the quantum realm. Superposition is not just a mathematical tool for physicists, it is an invitation to see the world, and ourselves, not as a collection of fixed, solid objects, but as a dynamic, vibrant, and endlessly creative sea of possibilities. The transition from the probabilistic, superpositional world of quantum mechanics to the definite, classical world of our everyday experience is known as the collapse of the wave function, and it lies at the heart of the quantum measurement problem. The wave function is the mathematical object that describes the probability cloud of a quantum system. It contains all the information about all the possible states the system can be in. As long as the system is isolated, the wave function evolves smoothly and predictably according to the Schrödinger equation, a continuous, wave-like evolution. But the moment a measurement is made, something dramatic and discontinuous happens. The wave function instantaneously collapses, and only one of the many possibilities becomes the single, actual reality. This collapse is not described by the Schrödinger equation. It is a separate, ad hoc rule that we have to add to the theory to make it match our observations. But what constitutes a measurement? What is the magical ingredient that causes this collapse? This is the question that has divided physicists for a century. The Copenhagen interpretation, the historical orthodoxy developed by Niels Bohr and Werner Heisenberg, takes a pragmatic and somewhat mysterious view. It posits a fundamental split between the quantum world and the classical world of our measuring devices. When a quantum system interacts with a classical measuring device, the collapse just happens. The interpretation does not explain how or why it happens, it simply states that it does, and that our job as physicists is to calculate the probabilities of the different outcomes. This is a deeply unsatisfying answer for many, as it leaves the boundary between quantum and classical ill-defined and elevates measurement to a special, almost mystical, status. In response to this dissatisfaction, other interpretations have been proposed. The many worlds interpretation, first proposed by Hugh Everett III, offers a radical and elegant solution. There is no collapse. The wave function never collapses. When a measurement is made, all possible outcomes actually happen. The universe itself splits or branches into multiple parallel universes, one for each possible outcome. In one universe, the atom in Schrödinger's box decays and the cat is dead. In another, it does not, and the cat is alive. The observer also splits, with one version of you seeing the dead cat and another version seeing the living one. In this view, measurement is not an act that collapses reality, it is an act that entangles the observer with the system, splitting the world into different, non-communicating branches. There is no special measurement process, there is only the smooth, continuous evolution of the universal wave function. Another class of theories, known as objective collapse or spontaneous collapse models, proposes that the collapse is a real physical process. It is not caused by an observer, but happens spontaneously and randomly. For a single particle, this spontaneous collapse is incredibly rare, but for a macroscopic object, which consists of a vast number of particles, the probability of one of them collapsing becomes incredibly high, leading to an almost instantaneous collapse of the entire object's wave function. This is why we never see macroscopic objects like cats in a superposition. They are simply too large and complex to maintain their quantum coherence for any significant amount of time. The measurement problem remains one of the most profound and open questions in all of science. It is a question that probes the very nature of reality, the role of the observer, and the boundary between the potential and the actual. And it is a question that resonates with the experience of falling asleep. As we close our eyes and turn our attention inward, the constant stream of measurements from the external world ceases. The neural windows of perception close, and our consciousness is no longer being constantly collapsed by the influx of sensory data. It is in this state of sensory deprivation that the mind is free to explore its own internal quantum universe, a universe of uncollapsed possibilities, of fluid associations, of dream-like superposition. The act of sleeping is, in a sense, a voluntary suspension of the measurement process, an act of surrendering to the pure, uncollapsed potential of our own consciousness. The inherent fuzziness of the quantum world, the fact that a particle can be in many places at once, is inextricably linked to another fundamental principle, Heisenberg's uncertainty principle. This principle is not a statement about the limitations of our measuring devices. It is a fundamental, built-in property of the universe itself. It states that there are certain pairs of physical properties, known as conjugate variables, that cannot both be known with perfect precision at the same time. The most famous of these pairs is position and momentum. The more precisely you measure the position of a particle, the less precisely you can know its momentum, and vice versa. There is an irreducible trade-off, a fundamental limit to our knowledge. Imagine trying to measure the position of an electron. To see it, you have to bounce something off of it, like a photon of light. To get a precise measurement of its position, you need to use a photon with a very short wavelength, which means it has a very high energy. But when this high-energy photon hits the electron, it gives it a powerful kick, changing its momentum in an unpredictable way. The very act of measuring the position has made the momentum uncertain. Conversely, if you want to measure the momentum precisely, you need to use a low-energy photon, but this has a long wavelength, which gives you a very fuzzy, imprecise measurement of its position. It is a cosmic game of catch-22, a game we can never win. This principle is not just a theoretical curiosity, it has profound and tangible consequences. It is the reason that atoms are stable. If an electron could have a precise position and zero momentum, it would just sit at the bottom of the atom's potential well, right on top of the nucleus. But the uncertainty principle forbids this. If its position were perfectly known, its momentum would be infinitely uncertain, meaning it could have a huge velocity, and it would not stay there. Instead, the electron exists in a probability cloud around the nucleus, a compromise between being close to the nucleus and having a spread-out position. The uncertainty principle is also the source of the zero-point energy of the vacuum, the ever-present quantum jiggle that prevents anything from ever being truly still. And it has a deep and beautiful echo in our own mental and emotional lives. We can focus intently on one aspect of our experience, a single thought, a specific feeling, a detailed plan for the future. But the more we focus on that single point, the more the vast landscape of other possibilities, other feelings, other potential futures becomes uncertain and fuzzy. We can know the what of our present moment with great clarity, but in doing so, we lose sight of the where-to of our potential paths. As we prepare for sleep, this mental uncertainty becomes a palpable experience. We try to hold on to a single thought, to solve a problem, to plan the next day. But the more we try to pin it down, the more other thoughts and feelings intrude, pulling us into a state of fluid, associative thinking. The conscious, controlling mind begins to lose its grip, and we are drawn into the gentle, welcoming embrace of uncertainty. This is not a failure of control, it is a necessary surrender. It is in this state of mental uncertainty that the creative, restorative processes of sleep can begin. The mind is no longer confined to a single track, but is free to explore the vast, interconnected web of memories, emotions, and possibilities that make up our inner world. The uncertainty principle, at both the quantum and the psychological level, is not a limitation on our knowledge, but an opening to a deeper, richer, and more creative form of existence. It is the universe's way of telling us that not everything can or should be known with perfect certainty, and that in the spaces between our knowledge, in the gentle fog of the unknown, lies the true source of all creativity and all change. Perhaps the most spooky and counterintuitive of all quantum phenomena is entanglement. It is a strange and intimate connection that can exist between two or more particles, a bond so deep that it seems to transcend the normal rules of space and time. When two particles, like a pair of photons, are created in a certain way, their quantum states can become entangled. This means that they are no longer independent entities, but are part of a single, unified quantum system, described by a single wave function. The strange part is that this connection persists no matter how far apart the particles are separated. If you take these two entangled photons and send them to opposite ends of the galaxy, they will remain linked. The real spookiness comes in when you make a measurement. According to quantum mechanics, a property of a particle, like its polarization, is not determined until it is measured. It exists in a superposition of all possible polarizations. But with an entangled pair, the moment you measure the polarization of one photon and find it to be, say, vertical, you instantly know that its distant partner, light years away, will be found to be horizontal if you were to measure it. It is as if the first photon's measurement result is instantaneously communicated to the second, in a way that seems to violate Einstein's cosmic speed limit, the speed of light. Albert Einstein famously disliked this aspect of quantum mechanics, derisively calling it spookhafte Fernwirkung, or spooky action at a distance. He believed that this apparent faster-than-light communication was a sign that the theory was incomplete, that there must be some hidden local variables that the particles carried with them, predetermining the results of the measurements. For decades, this was a philosophical debate. But in the 1960s, the physicist John Bell devised a clever mathematical theorem, now known as Bell's theorem, which showed that it was possible to experimentally distinguish between the predictions of quantum mechanics and any theory based on local hidden variables. In the decades since, numerous Bell test experiments have been performed with increasing precision, and every single one of them has confirmed the predictions of quantum mechanics and ruled out local hidden variable theories. The spooky action is real. The universe is, in some fundamental way, non-local. This does not mean that we can use entanglement to send faster-than-light signals. A measurement on one particle is random. You cannot control whether you get vertical or horizontal. You only know that your friend at the other end of the galaxy will get the opposite result. It is only when you later compare your results, a process that is still limited by the speed of light, that you can see the correlation. But the underlying connection is still instantaneous and profound. It suggests that at a deep level, the universe is not a collection of separate, isolated objects, but a single, holistic, and interconnected whole. This has deep philosophical and even spiritual resonances. Could the feeling of connection we sometimes have with a loved one far away, the sense of empathy that can span continents, the feeling of being part of a collective consciousness, be a macroscopic echo of this fundamental quantum entanglement? As we fall asleep, our sense of a separate, bounded self begins to dissolve. The rigid walls of our individual consciousness become more porous. In the dream state, physical distance often loses its meaning. We can be with people who are long gone or far away. We can feel their presence, hear their voice, experience their emotions. Perhaps in this state, our minds are more attuned to the subtle, the non-local connections that bind us to the people in the world around us. Perhaps sleep is a time when the brain's classical processing gives way, and we become more sensitive to the spooky action of our own entangled emotional and relational fields. Entanglement tells us that separation is, in some sense, an illusion. It is a powerful reminder that we are all part of a single, vast, and mysterious quantum system. A system where the connections are deeper and more profound than our classical intuition can ever fully grasp. And in the quiet intimacy of sleep, we may get our closest glimpse of this fundamental cosmic unity. The thought experiment of Schrödinger's cat serves as a powerful and enduring metaphor for the bizarre and counterintuitive nature of the quantum world. By taking the concept of superposition out of the abstract realm of subatomic particles and applying it to a familiar, macroscopic object, Schrödinger forces us to confront the profound weirdness of quantum reality head-on. The cat in the box, suspended in a ghostly state between life and death, becomes a symbol for the fundamental uncertainty and probabilistic nature that lies at the heart of existence. It is a story that highlights the central role of the observer in shaping reality. The cat's fate is not decided until we look. This raises deep questions about the nature of objectivity. Is there a world out there that exists independently of our perception of it? Or is the universe a participatory one, where the act of conscious observation is what brings reality into being? This is not just a scientific puzzle, it is an existential one. It challenges our sense of being passive spectators in a predetermined universe and suggests that we are, in a very real sense, co-creators of our own reality. This idea finds a powerful echo in our own psychological lives. We all have Schrödinger's cats in our own minds, unexamined fears, unresolved conflicts, unspoken desires, potential futures that we hold in a state of superposition. As long as we keep the box of our consciousness closed, as long as we avoid confronting these issues, they exist in a state of limbo. A difficult conversation we need to have is both had and not had. A life-changing decision is both made and not made. These uncollapsed potentials can create a constant, low-level anxiety, a sense of being stuck. The act of opening the box, of facing the fear, of making the decision, of speaking the truth is what collapses the wave function of our own lives. It can be a painful and difficult process, as we may not like what we find inside, but it is also a necessary one, as it is the only way to move from a state of uncertain potential to a state of definite reality. In this sense, the process of psychological growth and self-awareness is a process of consciously and courageously opening the boxes we have kept sealed within ourselves. Sleep and dreams provide a unique and often powerful arena for this process. In the safety of the dream state, where the stakes are not real, We can often confront our inner Schrödinger's cats in a symbolic form. We can face the monsters that represent our fears. We can explore the alternative paths that represent our unmade decisions. We can live out the consequences of our suppressed desires. Dreams are a kind of nightly, unconscious therapy, a process where the mind rehearses the act of opening the box, of collapsing the wave functions of our own psyche. The state of falling asleep itself is like entering the box. We leave the world of definite, classical reality and enter a liminal space of possibility. The last thoughts before sleep are often a superposition of the day's events and the next day's anxieties, a jumble of memories and anticipations. We are suspended, like the cat, between the past and the future, between what is and what could be. And in the dream state, we are free to explore all of these possibilities. We can see the cat both alive and dead. We can live out both the best case and the worst case scenarios. This is why sleep is not just a passive state of rest, but an active, creative, and transformative process. It is a nightly journey into the quantum heart of our own being, a journey where we confront our uncertainties, explore our potentials, and ultimately prepare ourselves to open the boxes of our own lives when we wake. The ability of a quantum particle to tunnel through a barrier that it classically should not be able to overcome is another of nature's deep and beautiful mysteries. In the classical world, if you throw a ball at a wall, it will either have enough energy to go over the wall or it will bounce back. It will never be found on the other side of the wall if it didn't have enough energy to clear it. But in the quantum world, things are different. A particle, like an electron, is not a solid point, but a wave of probability. And this wave does not stop abruptly at a barrier. It decays exponentially into it. If the barrier is thin enough, there is a small but non-zero probability that the wave will have some amplitude on the other side. This means there is a finite chance that the particle, when measured, will be found on the far side of the barrier, having seemingly tunneled through an impossible obstacle. This is not just a theoretical curiosity. It is a phenomenon that is essential to the functioning of our universe. The sun shines because of quantum tunneling. In the core of the sun, the temperatures are not quite high enough for hydrogen nuclei to overcome their mutual electrostatic repulsion and fuse together in the way that classical physics would require. It is only because of quantum tunneling that they can get close enough for the strong nuclear force to take over and initiate the process of nuclear fusion, releasing the energy that powers our solar system. Quantum tunneling is also at the heart of many of our modern technologies. In a scanning tunneling microscope, a sharp metal tip is brought incredibly close to a surface, and the tiny quantum tunneling current that flows between the tip and the surface is used to create an image of the individual atoms on that surface. The flash memory in our computers and smartphones works by trapping and releasing electrons in a floating gate through a thin insulating barrier, a process that is only possible because of quantum tunneling. But beyond its role in physics and technology, quantum tunneling is a powerful metaphor for the human experience of overcoming obstacles. We all face barriers in our lives: fears, self-doubts, limiting beliefs, societal pressures, past traumas. These can seem like solid, impenetrable walls, and classical, logical thinking can often lead us to believe that they are insurmountable, but the human spirit, like a quantum particle, has a wave-like nature. Our consciousness, our creativity, our resilience are not confined to a single point. We have the capacity to find unexpected paths, to tunnel through the obstacles that seem to block our way. This often happens not through brute force, but through a shift in perspective, a moment of insight, a creative leap of faith. And sleep and dreams are often the crucible where this mental tunneling takes place. In the dream state, the rigid, logical barriers of the waking mind are softened. We are free to explore unconventional solutions, to make associative leaps that our rational mind would dismiss. A problem that seemed intractable during the day can suddenly find a resolution in a dream, not through a step-by-step logical process, but through a sudden, intuitive tunneling to a new perspective. We can wake up in the morning with a strange sense of clarity, a feeling of lightness, a new way forward that was not apparent the night before. This is the power of the unconscious mind to find its way through the walls of our own making. Quantum tunneling is the universe's way of telling us that no barrier is absolute. It is a message of hope, a whisper from the subatomic world that even when the way seems blocked, there is always a possibility, however small, of a breakthrough. It is an invitation to trust in the wave-like, creative, and unpredictable nature of our own being, and to remember that sometimes the only way through is through. The principle of superposition, the idea that a quantum system can exist in multiple states at once, is not just a statement about the properties of individual particles. It is a profound statement about the nature of reality itself. It tells us that the universe, at its most fundamental level, is not a collection of definite fixed things, but a dynamic, vibrant, and multi-layered web of possibilities. Reality is not a single, monolithic entity, but a superposition of all possible realities. This is a concept that is deeply challenging to our classical intuition, which is built on the either-or logic of our macroscopic world. A door is either open or closed, a person is either here or there, but the quantum world operates on a both-and logic. An electron is both a wave and a particle. A cat is both alive and dead. This multiplicity of existence is not something we can directly perceive, because the act of perception itself, the act of measurement, forces a choice. The wave function collapses, and one of the many possibilities becomes the single, experienced reality. But the underlying, unobserved reality remains a rich and complex superposition. This has a powerful and beautiful resonance with our own inner lives. The human mind is not a single, unified consciousness. We are a superposition of multiple selves, multiple desires, multiple beliefs, multiple potential life paths. We contain multitudes, the you who goes to work in the morning, the you who laughs with friends, the you who feels a deep sense of sorrow in a quiet moment. These are all different states, different aspects of a single, complex wave function of the self. We often experience this as internal conflict or indecision. We want both to pursue a safe, stable career and to follow a risky, artistic passion. We feel both love and resentment towards the same person. These are not signs of a flawed or broken psyche. They're the natural expression of our own inner quantum superposition. And nowhere is this multiplicity more apparent than in the dream state. Sleep is the nightly dissolution of the collapsed self of our waking life. The ego, the sense of a single, continuous identity, loosens its grip, and the vast superpositional nature of our consciousness is allowed to come to the fore. In dreams, we can be anyone, anywhere, anytime. We can be a child again, feeling the pure, unadulterated joy of a long-lost summer afternoon. We can be a king, a pauper, a bird, a fish. We can experience the world from a completely different perspective, inhabit a different body, live a different life. These are not just random, meaningless images. They are the exploration of our own, uncollapsed potential. They are the whispers of our other possible selves. Dreams are the theater of superposition, a stage where all the different versions of who we are, who we have been, and who we could be are allowed to play out their parts. This is why dreams can be so liberating and also so unsettling. They show us that our waking identity is just one of many possibilities, one collapsed state among an infinity of others. Superposition, at both the quantum and the psychological level, is a reminder that reality is far richer, more complex, and more mysterious than our everyday. Classical mind can comprehend. It is an invitation to embrace our own multiplicity, to honor the different and sometimes contradictory parts of ourselves, and to remember that even when we have made a choice and collapsed our reality into a single path, the echoes of all the other paths, all the other possibilities are still there, vibrating silently in the deep, superpositional sea of our own being. The phenomenon of radioactive decay provides a fascinating window into the quantum nature of time. A radioactive atom, like the one in Schrödinger's thought experiment, is an unstable system. Its nucleus has an excess of energy, and it will eventually decay, transforming into a more stable nucleus and emitting a particle. But the when of this decay is fundamentally unpredictable. We cannot, even in principle, know the exact moment that a particular atom will decay. All we can know is its half-life, the time it takes for half of a large sample of these atoms to decay. For a single atom, the moment of decay is a purely probabilistic event. It could happen in the next second, or it could happen in 1,000 years. Time. At this fundamental level, does not seem to be a smooth, deterministic flow, but a series of probabilistic quantum jumps. This state of waiting, of existing in an unstable state with a potential for transformation, is a profound metaphor for the nature of time itself. It suggests that time is not a river that carries us along at a constant speed, but a landscape of potential, where events are not predetermined, but are realized through the resolution of quantum uncertainty. The moment of decay is the moment when a possibility becomes an actuality, the moment when the wave function of the atom collapses from a superposition of undecayed and decayed into a single, definite state. Before that moment, the future is open. After that moment, the past is fixed. The decay event is a now, a point where the fog of quantum probability crystallizes into the hard fact of classical reality. This resonates deeply with our own subjective experience of time, especially in the state of falling asleep. As we drift into slumber, our rigid clock-time perception of the world begins to dissolve. The linear progression of thoughts gives way to a more fluid, associative state. Time becomes fragmented, non-linear. A 5-minute doze can feel like an hour. A long night of deep sleep can feel like it passed in an instant. In dreams, the arrow of time can be completely abandoned. We can relive moments from our distant past or experience vivid, detailed scenarios of a potential future. The mind, in this state, is operating on quantum time, a time that is not measured by the ticking of a clock, but by the unfolding of meaningful, emotional events. The decay of an atom is a physical transformation, but we also experience a form of mental decay in our own lives. A long-held belief can suddenly crumble in the face of a new experience. A deeply ingrained emotional pattern, a half-life of sorrow or anger, can suddenly transform, releasing us into a new, more stable state of being. These moments of insight and transformation are often not the result of a slow, linear process, but of a sudden, unpredictable quantum leap in our consciousness. And very often, the seeds of these transformations are sown in the quiet, timeless realm of sleep. Sleep is a state where we let go of our attachment to the linear, forward-moving narrative of our lives. We allow our consciousness to decay, to dissolve its rigid structures, and to be reborn in the morning. Time does not age us. It is our passage through the landscape of possibility, our constant process of collapsing the wave function of our own lives. That shapes who we are. The universe, at its core, is a story of transformation and decay. In all its forms, is the engine of that story. The wave-particle duality is perhaps the most central and profound paradox of the quantum world. It is the seemingly impossible fact that the fundamental constituents of our universe entities, like electrons and photons, behave sometimes like localized, solid particles, and other times like spread-out, ethereal waves. This is not a matter of them being one or the other, and we are just unsure which they are. In a deep and fundamental sense, both. Their nature is not a fixed property, but is dependent on the context of the experiment, on the question we ask of them. If we design an experiment to measure their position, to see which slit they go through, they behave like particles. If we design an experiment to observe their interference pattern, to see how they spread and interact, they behave like waves. The universe, it seems, responds to our inquiry. Our choice of measurement determines the reality we perceive. This is a radical departure from the classical, Newtonian worldview, where reality is a fixed, objective thing that exists independently of our observation. The quantum world suggests a more participatory reality, a reality that is co-created in the act of interaction. This duality is not just a feature of the subatomic world, it is a powerful metaphor for our own existence. We, too, live in a state of wave-particle duality. In our waking, everyday lives, we are particles. We have a specific location in space and time. We have a defined identity, a name, a body, a set of roles and responsibilities. We interact with the world as separate, discrete entities. But in other states of consciousness, in deep meditation, in moments of creative flow, in the throes of love, and most universally, in sleep, we experience our wave nature. Our sense of a separate, bounded self dissolves, and we feel a sense of connection to something larger. Our consciousness is no longer a localized point, but a spread-out field of awareness. Sleep is the nightly immersion into our wave-like being. As we drift off, the particle-like identity of our ego, with its sharp boundaries and constant self-monitoring, begins to fade. The borders of the self become porous. We are no longer just me, a single, isolated point of consciousness. We become a flow, a stream of images, feelings, and memories that are not bound by the normal rules of time, space, and identity. In dreams, we are the ultimate wave. We can be in multiple places at once. We can merge with other characters. We can experience a reality that is fluid, symbolic, and associative. The rigid logic of the particle gives way to the poetic, interconnected logic of the wave. This nightly oscillation between our particle self and our wave self is not just a biological necessity, it is an essential part of our psychological and spiritual health. It is a process of rebalancing, of remembering that we are not just our egos, not just the sum of our worldly achievements and failures. We are also something more, something vast, interconnected, and mysterious. We are both the finite particle and the infinite wave. The wave-particle duality is the universe's way of telling us that reality is not a simple, one-dimensional thing. It is a rich, paradoxical, and beautiful mystery. And in the rhythm of our own lives, in the daily cycle of waking and sleeping, of being and flowing, we are living out this fundamental cosmic truth. We are particles of consciousness, dreaming that we are waves. The law of radioactive decay, with its inherent unpredictability, does more than just challenge our classical notions of time. It provides a profound insight into the very nature of its arrow. We experience time as a relentless, unidirectional flow, a river that carries us inexorably from the past to the future. The second law of thermodynamics, the law of entropy, provides a physical basis for this arrow. The universe as a whole tends to move from a state of order to a state of disorder. But the quantum world suggests a more subtle and nuanced picture. The decay of a single atom is not a process that happens in time. It is an event that creates a moment of time. Before the decay, the system exists in a timeless, probabilistic state of potential. The decay itself is the collapse of this potential into a definite, historical fact. It is the crystallization of now. This perspective suggests that the flow of time is not a smooth, continuous property of the universe, but is rather a staccato sequence of such irreversible, information-creating events. The universe builds its past, moment by moment, through the resolution of quantum uncertainty. This resonates with our own experience of consciousness. Our sense of a continuous flowing present is an illusion created by our minds. In reality, our consciousness is a series of discrete moments of awareness, strung together so quickly that they create the impression of a smooth flow. Sleep is a state where this illusion is temporarily suspended. The mind is no longer engaged in the constant process of creating nows from the sensory input of the external world. It is free to roam in the timeless, probabilistic realm of the unconscious. This is why our perception of time becomes so distorted in sleep. The mind is no longer bound by the relentless, forward-moving sequence of decay-like events that constitutes our waking reality. It is in a state of pure potential, a state more akin to the undecayed atom. But this is not a passive state. In this timeless realm, the mind is engaged in a different kind of work, a work of integration, of healing, of reorganization. The decay events of our waking life, the stressful encounters, the emotional shocks, the difficult decisions leave a residue in our psyche. Sleep is the process by which our minds metabolize these events, integrating them into the larger narrative of our lives. It is a form of mental decay, a process of letting go of the old and preparing for the new. The anxieties of the day can dissolve in the quiet of the night. A difficult memory can be transformed, its emotional charge neutralized. We wake up in the morning, not as the same person who went to sleep, but as a decayed product, a new version of ourselves that has been subtly but profoundly reshaped by the timeless work of the night. The arrow of time, then, is not just a physical law, it is a psychological and spiritual one. It is the story of our own constant transformation, our own continuous process of decaying and being reborn, a process that finds its most profound expression in the silent, mysterious, and deeply restorative alchemy of sleep. The quantum principle of superposition reveals a truth that extends far beyond the realm of subatomic particles. Reality is fundamentally multi-layered, and existence is a constant negotiation between possibility and actuality. This is not just a feature of the physical world, it is a deep and resonant truth about the nature of our own souls. We are not single, monolithic entities. We are a superposition of all our potential selves. The person you are today is just one collapsed state, one realized possibility from an infinite spectrum of potential yous. Every choice you have made, every path you have taken, has collapsed your wave function into a particular reality. But the other possibilities, the other paths, do not simply vanish. They continue to exist as a kind of quantum potential, a ghostly echo in the superpositional field of your own being. This is a concept that can be difficult to grasp intellectually, but it is one that we all experience intuitively, especially in the liminal spaces of our lives, in moments of deep reflection, in daydreams, and most powerfully, in our sleep. Sleep is the great decomposer of the singular self. The ego, with its need for a coherent, consistent narrative, relaxes its grip, and the multiplicity of the soul is allowed to emerge. In our dreams, we are not bound by the choices we have made in our waking lives. We can explore the roads not taken. We can be the artist we chose not to become, the lover we let go, the person we might have been if we had been born in a different time or a different place. These dream experiences are not just idle fantasies. They are the soul's way of exploring its own, vast superpositional landscape. They are a form of quantum exploration, a way of touching and integrating the other, potential versions of ourselves that coexist within our psyche. This is why dreams can be so emotionally powerful. They can bring a sense of profound longing for a life not lived, or a deep sense of gratitude for the life we have. They can show us aspects of ourselves, our courage, our creativity, our darkness that we have suppressed or disowned in our waking lives. They are a form of soul retrieval, a process of gathering the scattered fragments of our own potential and weaving them into a richer, the more complete sense of self. The idea that we are a superposition of souls also provides a new and beautiful way to think about our relationships with others. When we connect deeply with another person, we are not just two separate particles interacting. We are two complex wave functions, two superpositional fields, overlapping and entangling. We become part of each other's potential, the love, the wisdom, the pain we share become part of the superposition of each other's souls. This is why the loss of a loved one can feel like the loss of a part of ourselves, a part of our own superposition, a set of possibilities that was realized through our connection with them, has collapsed and is no longer accessible. But the entanglement remains. The connection, the influence, the shared possibilities continue to vibrate within the field of our own being, often surfacing in the quiet, superpositional space of our dreams. Quantum mechanics is often seen as a cold, abstract, and counterintuitive theory, but when viewed through this metaphorical lens, it becomes a source of deep, spiritual wisdom. It tells us that we are more vast, more complex, and more mysterious than we can ever fully know. It tells us that our lives are a constant dance between the many and the one, between the infinite sea of possibility and the single, precious, collapsed reality of our lived experience. And it tells us that sleep is a sacred time, a nightly pilgrimage to the superpositional heart of our own soul, a time to remember the infinite possibilities from which we have come and to which we will one day return. The observer effect in quantum mechanics is more than just a statement about the influence of measurement on a physical system. It is a profound revelation about the participatory nature of the universe. It tells us that reality is not a static, pre-existing canvas that we passively observe. It is a dynamic, interactive process, a cosmic dialogue between the potential and the actual, a dialogue in which the observer is a crucial participant. The universe, in a very real sense, is a mirror. It reflects back to us the nature of our own inquiry. If we ask it a particle question, we get a particle answer. If we ask it a wave question, we get a wave answer. This does not mean that reality is purely subjective, that we can create anything we want simply by wishing for it. The underlying probabilities are still governed by the rigorous mathematical laws of the wave function. We cannot change the odds, but our choice of what to measure, Our choice of which question to ask is what collapses those odds into a definite outcome. We are the deciders. This has a powerful and direct parallel in the way we construct our own personal realities. The world we experience is not a raw, objective feed of sensory data. It is a filtered, interpreted and co-created reality, shaped by the questions we ask of it, the beliefs we hold about it, the attention we pay to it. If we look at the world through a lens of fear and scarcity, we will tend to observe and amplify the evidence that confirms that view. The world will, in a sense, collapse into a state that matches our observation. If we look at the world through a lens of compassion and abundance, we will tend to observe and amplify the evidence for that reality. Our gaze is not passive, it is creative. It is a cosmic act, and this act of creation is not limited to our waking lives. Sleep is a time when the nature of the observer shifts, from the conscious, externally focused ego to the deeper, more symbolic intelligence of the unconscious. In our dreams, we are both the creator of the dream world and the observer within it. The landscapes, the characters, the narratives of our dreams are a projection of our own inner state, our own fears, desires, and unresolved conflicts. But they are not just a passive reflection. The way we interact with the dream, the way we observe it from within, can change its course. In a lucid dream, where we become aware that we are dreaming, this power becomes explicit. We can consciously choose to confront the frightening monster, and in doing so, we may find that it transforms into a helpful guide. We can choose to fly, and in doing so, we collapse the wave function of the dream world in a way that makes flight possible. Lucid dreaming is a powerful training ground for the participatory nature of reality. It teaches us that our awareness is a creative force, that our intention can shape our experience. But even in ordinary dreams, this process is at play. The dream is a constant feedback loop between the unconscious observer and the dream world it is creating. It is a dialogue, a dance. The observer effect, at both the quantum and the psychological level, is a call to a greater sense of responsibility. If our gaze helps to create the world, then we have a responsibility to look with wisdom, with compassion, with courage. We are not just insignificant specks of dust in a vast, indifferent cosmos. We are the universe's own organs of perception, the points at which the infinite potential of the quantum vacuum collapses into the lived, experienced, and meaningful reality of a conscious world. And every night, in the quiet, dark theater of our own minds, we are given the chance to rehearse this sacred creative act, to practice the art of observation, and to remember that the universe is not just something we are in, but something we are doing. The uncertainty principle, with its fundamental limit on our knowledge, is not a statement of failure or imperfection. It is a description of the inherent dynamic and musical nature of reality. It tells us that the universe is not a static and machine-like system that can be perfectly known and predicted, but a fluid, vibrant, and endlessly creative process. The trade-off between position and momentum is not a flaw. It is the source of all stability and all change. It is what prevents the universe from collapsing into a state of perfect static certainty. This principle, which governs the behavior of the smallest particles, is also a profound metaphor for the nature of our own minds and the process of living a creative and meaningful life. We often strive for certainty. We want to know the future, to control the outcome, to have a fixed and stable sense of who we are. We want to know both our precise position in life, our identity, our status, our place in the world, and our momentum, our direction, our purpose, our path forward. But the uncertainty principle suggests that this is an impossible and perhaps even undesirable goal. The more we try to fix our identity, to cling to a rigid sense of self, the more we lose our sense of direction, our capacity for movement and change. Our momentum becomes uncertain. We become stuck. Conversely, the more we focus on a single linear path forward, the more we can lose touch with our present reality, with the richness and complexity of our position in the here and now. We become ungrounded, disconnected. A healthy, creative life, like a stable quantum system, is a dance between these two poles. It is a process of finding a dynamic equilibrium between being and becoming, between rootedness and movement, between knowing who we are and being open to who we might become. Sleep is the nightly immersion into this dance of uncertainty. As we drift off, the controlling, certainty-seeking ego relinquishes its grip. We let go of our need to know, to define, to predict. We surrender to the unknown, and in this surrender, the mind is set free. Thoughts are no longer confined to a single logical track. They can move and associate in fluid and unpredictable ways. This is the state of hypnagogia, the creative, dreamlike state between waking and sleeping, a state that has been the source of inspiration for countless artists, scientists, and mystics. It is a state where the uncertainty is not a problem to be solved, but a space to be explored. In the dream state proper, this exploration becomes a full-blown symphony. The normal rules of logic, time, and space are suspended. We can be in multiple places at once. We can be different people. We can experience a reality that is built on the associative, poetic logic of the unconscious. This is not chaos. It is a different kind of order. An order based not on linear causality, but on emotional and symbolic resonance. It is the music of the mind, freed from the constraints of classical certainty. The uncertainty principle is not a pessimistic statement about the limits of our knowledge. It is a cosmic permission slip, an invitation to embrace the mystery, to dance with the unknown, to find peace not in the illusion of control, but in the wise and graceful surrender to the beautiful, unpredictable, and endlessly creative music of an uncertain universe. And every night, as we close our eyes and let go, we are attuning ourselves to this fundamental cosmic rhythm. The concept of the quantum vacuum, the idea that emptiness is not nothingness but a seething sea of potential, is perhaps the most profound and revolutionary insight of modern physics. It inverts our most basic, intuitive understanding of the world. We tend to think of things as being primary and space as being a secondary, passive container for those things. But quantum field theory tells us that the opposite is true. The field, the vacuum, the potential is primary. The things, the particles, the matter are secondary. Emergent phenomena, temporary ripples on the surface of this deep, energetic ocean. This is a worldview that has deep echoes in many of the world's mystical and philosophical traditions. The Buddhist concept of sunyata, or emptiness, for example, is not a nihilistic concept of non-existence. It is the understanding that all phenomena are devoid of any intrinsic, independent existence, that they are all interconnected and arise from a common, underlying ground of being, a ground that is often described as a luminous, creative void. The Tao Te Ching speaks of the Tao as the empty and unnameable source from which the 10,000 things arise. These ancient intuitions, born from deep contemplative inquiry, seem to be pointing towards the same fundamental truth that modern physics is now uncovering through the language of mathematics and experimentation, that at the heart of reality lies a creative, potent, and generative emptiness. Sleep is our nightly, personal journey into this creative void. As the external world of things fades away, as the internal world of thoughts and ego structures dissolves, we are left with the pure, undifferentiated potential of our own consciousness. This can, at first, feel like a frightening loss of self, a descent into darkness and nothingness. But if we can learn to trust this process, to surrender to this inner emptiness, we can find that it is not a void of non-being, but a womb of recreation. It is in this silent, empty space that the restorative and healing processes of the psyche take place. The fragmented parts of ourselves are integrated. The emotional wounds of the day are cleansed. The creative seeds of new ideas and new perspectives are sown. Dreams are the first sprouts that emerge from this fertile ground. They are the first forms that crystallize out of the formless potential of the unconscious. They are the virtual particles of the psyche, bubbling up from the inner quantum vacuum, giving us glimpses of the creative processes that are at work in the depths of our being. This understanding of emptiness as a creative potential can be a powerful antidote to the fear and anxiety that often accompany the dark, quiet, and empty spaces of our lives, both literally and metaphorically. The moments when we feel lost, when our old identity is crumbling, when the future seems like a blank, empty canvas. These are not just moments of crisis, they are also moments of immense creative potential. They are moments when we are closest to the quantum vacuum of our own being, the source from which all new realities can be born. To fall asleep is to practice this surrender, to consciously and willingly enter the creative void. It is an act of faith in the generative power of the unknown, an act of trust that from the deepest silence, a new and more beautiful music will emerge. The quantum vacuum is the universe's ultimate secret, and it is a secret that is not hidden in some distant galaxy, but is present here and now, in the space between our thoughts, in the silence between our breaths, and in the deep, dark, and wonderfully creative emptiness of our own sleep. The non-local connection of quantum entanglement, the spooky action at a distance that so troubled Einstein, is more than just a bizarre feature of the subatomic world. It is a fundamental statement about the nature of reality. It tells us that the universe is not a collection of separate, billiard ball-like objects that interact only through local forces. It is a single, indivisible, and holistic system, where the parts are so deeply interconnected that the concept of separation itself becomes an illusion. The two entangled photons, light years apart, are not two separate things. They are two aspects of a single, unified quantum state. To measure one is to measure the whole system. This profound unity is a truth that is often obscured by our classical, macroscopic experience, where things appear to be separate, distinct, and localized. But the quantum world reveals the deeper underlying reality of interconnectedness. This has powerful and beautiful implications for our understanding of ourselves and our relationships. We are not isolated islands of consciousness. We are entangled beings, connected to the people we love, to the natural world around us, and to the cosmos as a whole, through a web of invisible, non-local bonds. These connections are not just metaphorical, they may have a real physical basis in the quantum nature of our own being. The feeling of empathy, the ability to feel what another person is feeling, the strange synchronicity of thinking of someone just before they call, the deep, unspoken bond between a mother and her child. These are all experiences that defy a purely classical, mechanistic explanation. They hint at a deeper level of connection, a form of conscious entanglement that operates outside the normal constraints of space and time. Sleep is a state where we are particularly open to experiencing this entangled reality. As the conscious mind, with its focus on separation and individuality, quiets down, the deeper, more holistic intelligence of the unconscious comes to the fore. In our dreams, the boundaries between self and other often dissolve. We can merge with other people. We can become animals or objects. We can experience a reality from a perspective that is not our own. We can have vivid, emotionally resonant dreams about people we are deeply connected to, even if they are far away. These are not just psychological phenomena. They may be the subjective experience of our own, real, quantum entanglement with the world. They are moments when our consciousness taps into the underlying unity of the cosmos, the single wave function that describes all of reality. This perspective can bring a profound sense of comfort and meaning. It tells us that we are never truly alone. Even in our most solitary moments, we are part of a vast, interconnected web of existence. The people we have loved and lost are not gone in an absolute sense. The entanglement, the connection, the shared information persists in the quantum field of the universe and can still be accessed in the non-local realm of our dreams. Quantum entanglement is the universe's most beautiful and mysterious secret. It is the physical basis for the spiritual truth that we are all one. And every night, as we surrender to the mystery of sleep, as we let go of our sense of a separate self and dissolve into the dream sea of the unconscious, we are returning home to this fundamental, entangled unity. We are remembering, at the deepest level of our being, that we are not just in the universe, but that we are the universe, experiencing itself, connecting with itself, and dreaming of itself. The dual nature of light, its ability to be both a continuous, spreading wave and a discrete, localized particle, is not a contradiction. It is a paradox that reveals the deep, complementary nature of reality. The principle of complementarity, first articulated by Niels Bohr, states that these two aspects of reality, the wave and the particle, are mutually exclusive. Yet both are necessary for a complete description of the phenomenon. You cannot see both aspects at the same time, but you need both to understand the whole. The choice of experiment determines which face of reality is revealed. This is a profound philosophical insight that extends far beyond the realm of physics. It suggests that reality is not a single, monolithic thing, but a dynamic interplay of opposing, yet complementary, principles. We see this duality everywhere in our own lives, light and shadow, order and chaos, being and becoming, masculine and feminine, conscious and unconscious. A full, integrated life is not about choosing one and rejecting the other. It is about learning to hold the tension between these opposites, to dance with the paradox. And nowhere is this dance more apparent than in the daily rhythm of our own consciousness. Our waking life is the particle aspect of our being. We are focused, localized, and goal-oriented. We interact with the world as separate, discrete individuals. We operate in the realm of linear time, of cause and effect, of either-or logic. Our consciousness is like a focused beam of light, illuminating a single point of reality, but our sleeping life is the wave aspect of our being. The focused, particle-like ego dissolves, and our consciousness spreads out, becoming a diffuse to non-local field of awareness. We are no longer bound by the constraints of linear time or a single identity. We operate in the realm of myth, of symbol, of both and logic. Our consciousness is like a spreading wave, interfering with itself, creating complex patterns of meaning and emotion, these two states of being, the waking and the sleeping. The particle and the wave are not opposed to each other. They are complementary. They are two essential parts of a single, whole human experience. The waking life provides the structure, the action, the engagement with the world. The sleeping life provides the context, the meaning, the connection to the deep, underlying currents of the psyche and the cosmos. Without the focused action of the particle, the wave remains a field of unmanifested potential. Without the deep, integrative wisdom of the wave, the particle becomes a disconnected, meaningless point. We need both. The health of our psyche depends on the graceful, rhythmic oscillation between these two modes of being. To honor our sleep, to value our dreams, is to honor the wave-like aspect of our own nature. It is to recognize that we are not just the solid, definite things we appear to be in the light of day, but also the fluid, mysterious, and infinitely interconnected waves we become in the darkness of the night. The wave-particle duality is not just a paradox of physics, it is the fundamental rhythm of life itself, a rhythm that we are privileged to experience in the most profound and personal way. Every time we close our eyes and surrender to the gentle, wave-like embrace of sleep, the incessant, energetic hum of the quantum vacuum, the constant bubbling of virtual particles in the midst of silence, is not a flaw in the universe's design. It is the very engine of its creativity. The void is not a static backdrop. It is a dynamic, living presence, a field of pure potential from which all forms arise and to which all forms return. This is a vision of the cosmos that is not mechanical and deterministic, but organic, spontaneous, and endlessly generative. The whispers of the vacuum are the first stirrings of existence, the premonitions of a universe waiting to be born. This understanding has a powerful and transformative echo in our own inner lives, the silent spaces of our own consciousness, the moments between thoughts, the pauses in conversation, the quiet stillness of meditation, the deep emptiness of sleep are not voids of non-existence. They are the most fertile ground for our own creativity, our own healing, our own transformation. We live in a world that is terrified of silence, of emptiness. We fill every moment with noise, with distraction, with activity. We are afraid that if we stop, if we become still, we will be confronted with a terrifying nothingness. But quantum physics, and the wisdom of the contemplative traditions, tells us that the opposite is true. It is in the silence that we can finally hear the subtle music of our own being. It is in the emptiness that we can touch the source of all our creativity. Sleep is our nightly mandatory pilgrimage to this inner sacred silence. As the noise of the day's events and the chatter of the conscious mind subside, we are given the chance to connect with the deep, quiet, generative vacuum of our own psyche. In this state, the mind is not passive, it is incredibly active, but in a different way. It is not engaged in the linear, logical processing of the waking state, but in the holistic, associative, and integrative work of the unconscious. It is in this inner silence that the fragments of our experience are woven into meaningful narratives. It is here that emotional wounds are processed and healed. It is from this fertile emptiness that the seeds of new ideas, new insights, and new solutions to our problems can spontaneously emerge. A dream is a virtual particle born from the vacuum of the mind. It is a fleeting, symbolic expression of the deep, creative processes that are at work in our inner silence. Sometimes these dreams are like the soft whispers of a gentle emotion. Other times they are like the powerful, transformative roar of a deep, archetypal insight, but they all arise from the same source, the potent, creative, and endlessly mysterious emptiness that lies at the heart of our own being. To learn to value silence, to befriend our own inner emptiness, to trust in the wisdom of our own sleep, this is to align ourselves with the most fundamental creative principle of the universe. It is to understand that all true creation, whether of a galaxy, a work of art, or a new and more integrated self, is born not from frantic effort, but from a deep and patient listening to the silent, secret, and life-giving whispers of the void. The quantum nature of time, its refusal to be a simple, linear, and absolute flow, is one of the most profound and mind-altering implications of modern physics. It suggests that our everyday experience of time as a river carrying us inexorably from a fixed past to an open future is a powerful, but ultimately limited, human construction. At the fundamental level, the distinction between past, present, and future may be far more fluid and interconnected than our classical intuition allows. The phenomenon of retrocausality, or backward-in-time influence, which has been tentatively explored in some quantum experiments like the delayed choice quantum eraser, suggests that a choice made in the future can influence the state of a system in the past. This is not to say that we can send messages back in time to change history in the classical sense, but it does suggest that the relationship between cause and effect is not as straightforward as we assume. The universe may be a block of space-time, as Einstein's relativity suggests, where past, present, and future all exist simultaneously, and the flow of time is an illusion of our consciousness. Or it may be a probabilistic branching structure, where the future is a set of open potentials that can retroactively influence the path that was taken to get there. Whatever the ultimate picture, the quantum world tells us that time is not a rigid container, but a dynamic and participatory process. And nowhere do we experience this dynamic, quantum nature of time more directly than in our dreams. Sleep is a realm where the linear chronological time of the waking world is completely abandoned. A dream can span decades in a matter of minutes. A moment of intense emotion can feel like an eternity. We can seamlessly transition from a vivid memory of our childhood to a fantastical vision of a distant future. The past is not a fixed record. It is a living, malleable presence that can be re-experienced, reinterpreted, and even healed. A dream can take a traumatic memory from the past and recontextualize it, allowing us to find a new meaning, a new resolution that was not available to our waking mind. The future is not a distant, unreachable shore. It is a field of potential that we can explore and interact with. A dream can present us with a symbolic preview of a challenge we are about to face, or offer an intuitive solution to a problem that has been troubling us. In the dream state, our consciousness is not a passenger on the river of time. It is the river itself. It can flow forwards, backwards, sideways. It can create eddies of memory, rapids of emotion, and deep, still pools of timeless insight. This is not just a psychological curiosity. It may be a direct, subjective experience of the fundamental, quantum nature of time itself. Our brains, as quantum biological systems, may be uniquely attuned to the nonlinear, probabilistic, and interconnected structure of space-time. To sleep is to step outside of the illusion of linear time and to enter into a more fundamental, more real relationship with the temporal fabric of the cosmos. It is a nightly reminder that the past is not gone, the future is not set, and the present moment is a point of creative potential where all times meet. The dreams we have are not just stories we tell ourselves, they are our soul's way of navigating the deep, mysterious, and beautifully quantum ocean of time. The existence of a multiverse, a vast, perhaps infinite ensemble of parallel universes, is one of the most extraordinary and mind-bending ideas to emerge from modern theoretical physics. It is not a single theory, but a consequence of several different lines of inquiry. From the many worlds interpretation of quantum mechanics to the theory of eternal cosmic inflation. In the many worlds picture, every quantum measurement, every probabilistic event causes the universe to split into multiple branches, one for each possible outcome. There is a universe where the atom in Schrödinger's box decayed, and a universe where it did not. There is a universe where you turned left at the intersection this morning, and a universe where you turned right. Every choice, every chance creates a new world. In the eternal inflation picture, our universe is just one bubble that nucleated from a vast, eternally expanding quantum vacuum, and other bubble universes, potentially with different physical laws and constants, are constantly being formed. This is a vision of reality that is almost incomprehensibly vast and rich. It suggests that our entire observable universe, with its billions of galaxies and trillions of stars, is just one grain of sand on an infinite cosmic beach. While we can never, even in principle, directly observe or communicate with these other universes, the idea that they exist has a profound impact on our understanding of our own. It provides a potential solution to the fine-tuning problem, and it forces us to confront the true scale of reality. But could we, perhaps, have an indirect connection to these other worlds? Could there be a subtle leakage of information? A faint echo from these parallel realities that we can perceive? This is where the nature of dreams becomes a fascinating area for speculation. Dreams are a realm where the impossible becomes possible, where the logic of our waking reality is suspended. We can encounter people we have never met, but feel a deep sense of familiarity with them. We can visit places that do not exist on any map, but which feel as real as our own home. We can experience lives that are not our own, with different histories, different relationships, different identities. Could it be that in the deep, non-local state of dream consciousness, our minds are capable of tapping into the universal wave function, the vast superpositional state that contains all of these parallel realities? Could a dream be a glimpse, a fleeting, symbolic echo of the life of an alternative self in a parallel universe? This is, of course, a highly speculative and unprovable idea, but it is a beautiful and compelling one. It would explain the profound sense of otherness and yet familiarity that so many dreams possess. It would account for the seemingly infinite creativity and novelty of the dream world. It would suggest that our consciousness is not confined to this single, collapsed reality, but has a deeper connection to the vast multiverse of possibility. In this view, sleep is not just a journey into our own personal unconscious. It is a journey into the cosmic unconscious, a nightly exploration of the infinite library of what could be, and what, in some other corner of the multiverse, actually is. To dream is to be a cosmic explorer, a traveler between worlds. And every morning, when we wake up, we return to our own, the specific branch of reality, perhaps carrying with us a faint, dreamlike memory of the other lives we are living, the other choices we have made, the other stories that are being told in the grand, and perhaps infinite, book of the cosmos. The ultimate mystery that the quantum world presents us with is the mystery of consciousness itself. As we have seen, the observer is not a passive bystander in the quantum drama, but a central and enigmatic character. The very act of observation seems to be what transforms the ghostly, probabilistic world of quantum potential into the solid, definite world of our classical experience. This has led some of the most profound thinkers in physics, from Schrödinger and Bohr to more contemporary figures like John Wheeler and Roger Penrose, to conclude that we will never have a complete theory of the universe until we have a theory of consciousness. The two are not separate problems. They are two sides of the same, deep mystery. The hard problem of consciousness, the question of how and why a physical system like the brain gives rise to the subjective, qualitative experience of being, the feeling of redness, the sound of a C-sharp. The feeling of love is perhaps the greatest unsolved problem in all of science. The classical mechanistic view of the brain as a complex biological computer has so far failed to provide a satisfactory answer. It can explain how the brain processes information, but not how it produces experience. This is where the quantum world offers a new, and perhaps more promising, avenue of inquiry. The quantum realm is not just about smallness, it is about a different kind of reality. a reality of holism, of interconnectedness, of non-locality, of unmanifested potential. These are properties that seem to resonate more closely with the nature of our own inner experience than the classical world of separate, solid objects. Perhaps consciousness is not an emergent property of classical computation in the brain, but is a fundamental the quantum phenomenon. Perhaps the brain is not a classical computer, but a quantum one, a biological instrument that has evolved to harness the strange and powerful properties of the quantum world to create the symphony of our subjective experience. In this view, the brain is not the source of consciousness. It is the receiver, the antenna that attunes itself to a more fundamental universal field of consciousness that pervades the entire universe. This would be a return, in a new, scientific guise, to some of the oldest ideas in human philosophy, the idea of a world soul or an anima mundi. Consciousness is not something that we have, it is something that we are, a localized expression of a cosmic principle. And sleep would be the state in which our individual, localized consciousness returns to and merges with this universal field. In the deep, dreamless state of slow-wave sleep, the ego dissolves, the sense of a separate self vanishes, and we are left with a state of pure, contentless awareness. This may be the closest we can come in our human experience to touching the ground state of consciousness itself, the quantum vacuum of the mind. And from this state, as we transition into the REM sleep of dreaming, new forms, new images, new narratives arise, like virtual particles bubbling up from the void. Dreams are the universe's way of exploring its own infinite imaginative potential through the unique individual lens of our own consciousness. This is a vision of reality that is both scientifically radical and spiritually profound. It suggests that our quest to understand the universe and our quest to understand ourselves are not two separate journeys, but one. The secrets of the cosmos are not just hidden in the hearts of distant stars or in the equations of theoretical physics. They are also hidden in the deep, silent, and mysterious nature of our own conscious awareness. To study the quantum world is to study the mind of God, as Einstein once said, and to study our own consciousness, to explore the depths of our own sleep and dreams, may be the most direct path we have to understanding the deep, quantum magic that underlies all of existence. The universe is not a dead, mechanical thing that happens to contain pockets of consciousness. The universe, at its most fundamental level, may be consciousness, and we are the dreams it is dreaming.